Hello, good morning to all dear participants. Hello, good morning to all. So for this session, Dr. Vishal Francis from LPU is with us. He is already joined the meet. Before inviting Dr. Vishal to deliver his talk, I will explain the some key features, or you can say the key lights of the Dr. Vishal Francis. He is working as an assistant professor in the School of Mechanical Engineering, Lovely Professional University, Punjab. He has obtained his PhD degree from IITM, Jabalpur, India. He has worked in the area of 3D printing of nanocomposite materials during his doctorate. He has organized and delivered many expert lectures at different platforms as well as at AICTE approved programs related to the 3D printing. He has more than 10 years of teaching experience, research and industrial experience, and has published many papers in the peer-reviewed reputed international journals, and so many more things he has developed as an article published in at the different platform. His area of interest is 3D printing, high performance material development for 3D printing, printed electronics and 3D printed prostheses. So with these words, I would like to invite Dr. Vishal Francis to deliver his talk. Welcome, sir. Vishal sir, now you can start.
Okay, thank you, sir. I think I am audible.
Yes, sir, you are audible.
Thank you, sir. So I'll just share my PPT, sir. Just give me 1 second.
Share.
I think my PPT is visible, sir. Is it visible?
Sir, PPT is not visible.
Okay, just. Okay, from my side, I have just shared. Now is it visible, sir?
No, sir. It is not visible. I think please check it again.
Okay, let Sir, now is it visible?
Not yet, sir.
Okay, okay, sir. Can you just check, because from my side it is saying that the sharing has started. Can you just, sir, check it?
Now it is visible.
Yes, sir. Yes, now it is visible. Yeah. Now it's fine.
Now it is visible.
Okay, sir. Okay, thank you, sir. Thank you. So I'll just start without further delay. I'll just start. Okay, so good morning, all participants, and welcome you for this session. And I'd like to congratulate Department of Industrial and Production Engineering, NIT Jalandhar, for organizing such an uh, worthwhile. You've selected a topic which is very important nowadays, and which is related to 3D printing and design with interdisciplinary applications, and giving me this opportunity to share some of the thoughts related to 3D printing, specifically related to the materials which are used in 3D printing. So we'll just start the session, and I hope the presentation is visible to all the participants. The voice is clear. In between, if you find any glitches, just let me know. Okay, so before we get into the today's topic, which is related to the material preparation for 3D printing and nano composite application, I just want to bring your attention to one of the case studies that I like to show you. One of the case study, just okay. So these are the names of few of the companies like Honda, Nissan, Mitsubishi, Suzuki. These are some of the automobile company, and we all are aware of these automobile companies. Some of us might be using the products which they are manufacturing. So it was a case of about 1980s or 1990, in the early 1990s, that these companies and other automobile manufacturer, they have to modify their restraint system, that is the seat belt system that we provide. Um, so, and this they have to do it in several modes of their vehicles. And this picture shows you the press release button, which was in the Takata 52 series buckle assembly. It is from 1987 Honda Accord. And these companies have to restrain this, they have to modify it, because there was a malfunctioning of this particular press release button. And these seat belt models were introduced in early 1986, and soon as it was reported that there are numerous complaints of the malfunctioning of the seat belt locking mechanism, locking and release mechanism. So they have to do this. So then they found out, once there was a malfunctioning, then they started investigating what was the reason for that. And when they found out they found out that this cross section which is shown on the screen, they saw that it was the broken one. The below one shows the broken, and the first one, the figure, shows the intact one. So this particular design failure was there. And then they tried to investigate investigate, and then they come up with the two possible problems that has caused. The first problem was because of the design. So people suggested that if you have provided the rib in reinforcement, it would have survived. So one category of people talked about the design, that there was a design failure, but then they also investigated the material that was used into that manufacturing. So this material was ABS material, polymer material. Now the problem with ABS was that it started degrading when it is exposed to UV rays. So other people talked about the problem which these companies faced was because of the selection of the material, because we know that automobiles, they are exposed to UV rays, and because of the degradation of the material, this malfunctioning would have occurred. So the point that I want to make over here before we start the our session, today's session, is that there are two things. First is the design and the material, and both of these two things are important whenever we go for product development. So when we talk about this material, so I want to take your attention toward the material point of view in today's lecture, that whenever if I have to develop a product, the selection of the material should be appropriate, because we want our product to function properly. Okay, having said this, let's start. So I'll talk about, quickly go through the 3D printing technology, the basics, the classification, and we'll start talking about the material. So I'll talk about the materials and the principles, phenomena which are used in various 3D printing processes, whether it's an extrusion based process, whether it's an powder based, or if whether it's a laser is used. So, and then we'll talk about the nanocomposites formation, how we can form the nanocomposite specifically for the extrusion based material. So let's start. So when we talk about 3D printing or additive manufacturing, it gives us a lot of advantages. That is the reason why people are preferring 3D printing over other manufacturing process. However, it has not replaced, we should be clear that it has not replaced other conventional manufacturing process, but this is it has proved itself, this technology has proved itself as a manufacturing technique, and people have started using it. So one of the things that it provides us is the design freedom. It provides us the design freedom, because if we talk about design for manufacturing, it says that do not design something which cannot be manufactured. But when we talk about design for additive manufacturing, it says that you can design anything, any complex part, doesn't matter. We can design any complicated part, whether it is if it is within the resolution of the machine will be able to print that if we design it properly. So it gives a lot of design freedom to the engineers, to the designers, and because of this, many sectors, many industries have embraced this technology, whether it is automobile technology or aerospace technology, and even in medical field we have seen. So these are the few things that I just wanted to show you. It gives us the design freedom, and it gives us innovation in healthcare. Nowadays, a lot of medical people have started using, this is one of the sector which have embraced additive manufacturing from its starting days, because now we can take the CT scan data, we can process the data, we can get a model out of it, a physical model within few hours or maybe days. We can get that model, and that can be used for various purposes. The surgeons are using it for pre-surgical planning. If they have a very complicated surgery that has to be taken, a tumor has to be removed or something like that, in that cases these 3D printing comes into very handy. And because we can just take the CT scan data, we can process those data, and we can get a CAD model, and once we have a CAD model, we can go for the printing of process. And it has impacted the manufacturing industries. So we'll see some of the industries in the coming slides, and it gives the ability to transform consumerism. That is, it helps us. It I can go for some very specific design which is suited for a particular person. So I can go for customization. And not only for customization, now because of this 3D printing, we can go for mass customization, which is not, I cannot go for mass customization using other conventional method, but this 3D printing technology gives us an ability to go for the mass customization. And this figure right here on which is regarding the on-demand printing shows you these walls which have been printed recently because of this COVID situation, where in Italy where there was a shortage of these valves which are used for the supply of the oxygen, and these valves were printed by 3D printing techniques. So on-demand printing, it also gives us the ability to get on-demand printing. We can quickly create a CAD model, or we can go for a reverse engineering procedure. If we have a product, we can get the data out of it, prepare a CAD model, and then we can go for 3D printing. Okay, so from these things, we have seen that in the last 3 decades, in the last around 30 years or so, we have seen that there is an technology which we used to refer as rapid prototyping has now been moved forward, and we have seen an evolution of this technique, rapid prototyping, and now we see that it has been used as in manufacturing. So from prototyping, now it is coming and taking a shape of a manufacturing technique itself. So we have earlier we used to use it for prototyping purposes only. However, now also we use it for prototyping purposes, but not only for prototyping purposes, because we can do a lot more things with this technology. So we can go for rapid tooling, and that has been used in automobile, medical sectors. We can go for manufacturing of end-use products, and nowadays even additive nano manufacturing is coming into picture, and we all might have heard about the bioprinting. So these are the terms which we generally use inter-exchangeably: additive manufacturing and 3D printing. So ASTM has given the definitions of the terminologies which we generally use. So it says that for additive manufacturing, it says it's define it as a process of joining materials to make object from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodology. However, when we talk about 3D printing more specifically, the definition says that the fabrication of objects through the deposition of material using a print head, nozzle, or other printer technology. So, but nowadays what we see that these two terms are used interchangeably. But more specifically, additive manufacturing is a group of technology. I would say it's a kind of an umbrella, and under that umbrella we have many different techniques. That, for example, we have fused deposition modeling, which nowadays we call it as fused filament fabrication, because the patent that was there in regarding FDM by Stratasys has been expired. So we have this fused filament fabrication, we have SLS, we have SLM, we have SLA, DLP, and so many other techniques are there. So all these comes under the umbrella of additive manufacturing. Okay, so let's move forward and let's talk about materials in this additive manufacturing technique. So as in other manufacturing, same is the case for additive manufacturing. The material plays a very important role. It's a building block for the 3D printing, because if I have very limited material with which I can actually do the processing, I can 3D print, then my application area, the domain of application will be very limited. But if I can process many materials, if I have a wide range of materials which can be processed, then I can also enlarge the application domain of that particular technology. So same is the case for 3D printing. So materials are the building block. If we can produce more materials, if we can develop more materials, innovative, high performance material, then we can actually enlarge the application domain of this particular technology. So these are few pictures which shows you about that. We can use it for functional testing and prototyping. We can use it for rapid tooling, and for medical we've talked about, and even now electronics also, because we can have, nowadays we have materials which are conductive materials which we can use for 3D printing process. And a lot of people are developing these materials. They are developing composites, nano composites, which give you more, they are more conductive in nature. Aerospace is one of the uh, area which has embraced this technology. The reason is because it gives a lot of design freedom, as we have talked about, and one can reduce the weight of that particular components which are there, which are used in aerospace aircraft. So if I can reduce the weight without compromising the performance of that particular part, then I can actually reduce the requirement of fuel consumption. And if I can reduce that, a lot of profit can be gained out of this. So these automobile companies are working in this direction. And the second thing is, any complex part can be manufactured with this technology. So the right one, if you see, this is the 3D printed fuel nozzle tip for the LEAP engine, which has been manufactured by GE Aviation, one of the companies that have that is using 3D printing for many applications. And on the left, if you see, that's new Airbus A350XWB aircraft. This contains around 1,000 3D printed parts. And as we have talked about, we can go for topology optimization, and we can reduce the volume. We can reduce a significant amount of volume from a component without sacrificing the performance of that particular component. And in this way, we can reduce the weight of that thing. So aerospace is one of the industries. And if we talk about aerospace, we have seen that NASA has also installed their this zero gravity 3D printers into one of its space centers there. And if we talk, the first instance of off-world manufacturing has been done by 3D printing itself. So in the space center, they have used this printer and they have 3D printed it, the particular thing. And even nowadays, a lot of students are involved into this. They use 3D printing to print, to fabricate the structure of the satellites. For example, for CubeSat that we call it, these 3D printed satellites. So they use the structure to manufacture the structure. They use 3D printing technique. And moving forward, automobile is another industry. This is another industry that uses 3D printing technique, and the application is a lot more in this case, ranging from functional prototyping, making molds, making jigs and fixtures, and even the components. So these are few of the examples I have taken, but these are not the limited. There are so many other examples. If you'll Google, you'll find it, that so many companies ranging from Mercedes and Audi and so many companies, they have started using 3D printing to use it in their production, in their manufacturing, in their design, various things. So this is one another sector which has embraced this particular thing. And how can we leave this medical, which has already embraced this technology? So we have medical devices which have been used, in which we use 3D printing technique, manufacturing of prostheses, implants, even in dentistry, and even in surgical planning and medical training we use it. So if you can see that this multicolor anatomical model, that is, see, this has been 3D printing by one of the technique. So we have 3D printers which can print with different materials, and even they can vary the you can say the hardness of that material. So we can get a very accurate model, even in terms of, not in terms only in terms of dimension, but in terms of its appearance also. So that can be used for medical training purposes, for surgical planning purposes. And if we can see this is the printed hand prosthesis, which was named by the inventor. He called it by the name of Cyborg Beast, and there's a story behind that. But we won't go into that story. But here he has proposed, this is a body-powered prosthesis which has been 3D printed. That is, no electronics are used, and also it gives a certain degree of functionality. And this is for people who are not able to afford the electronic prosthetic hand, so they can use this particular thing, and they can get some degree of functionality also. And this is just body powered, and basically it was designed and 3D printed for kids who are small and who actually over the period of time outgrow the prosthesis. So again, after a few years you have to purchase new ones. So this is the solution for those, and for people who cannot afford this. So this is uh, only possible because of this 3D printing technology, and this entire prosthetic hand can be printed within a day. Okay, so this can also be used for pre-operative surgical planning, because earlier the surgeon used to see the CT scan or maybe the X-rays, and seeing those things they plan their surgery. But now, what if we can take those data and take the CT scan data, and if we can process those data, we can get the CAD model, and by using 3D printing we can make the real part, a physical part, and that physical part can be used by the team of the surgeons, and they can plan their surgery. So it has been studied that this helps us, the surgeon, to in terms of surgery, in terms of the time that is required by the surgery, in terms of the blood loss and the recovery also. So this is one of the case study that I want to show. Just that this is the left mandible fracture of tibia. So this is a complex fracture. I think it has 4 to 5 fractures were there in the tibia plateau region, and the model was prepared within 6 to 7 hours, and that was used for the surgery in one of the hospitals. So this is one of the case study that I wanted to show you. And now, having said that, we know that it has, this particular technology has applications in various industries. So I have shown few of them. There are many more also. So the point by showing you this slide is that I want to bring your attention that it has been used by several types of industries, whether it's manufacturing, medical, and even in fashion industry, even in textile and jewelry. It is also being used, which I have not included, but it has been used. So there is a wide range of applications, where this technology is used. Okay, now coming to the materials, before that, let me just give a very basic generic overview of the AM process. So it starts with the creation of a solid model. The first we make a 3D model, a solid model, and we can make it directly by using any CAD packages. I can make it using any CAD packages, or I can go for reverse engineering. I can do reverse engineering, or I can take the CT scan data or any medical image data, and I can process this and make a CAD model. So whatever may be the route, the first step is to get a CAD model. And if we have a CAD model, we can proceed with the process of additive manufacturing or 3D printing. So, and then we generally convert it to an STL file, which is a standard triangulation language. What it does, it divides the entire surface into triangles, a number of triangles, and you will be learning this. You might have been knowing this. So there are various algorithms. So even if you just check any CAD packages, when we save the file, there is an option to save as an STL file. So this is the next step. And most 3D printers, they take this STL file. Nowadays, we have other format also which are used, but this is one of the kind of a de facto which has been used in 3D printing. So we get a CAD model and then we convert it into an STL file. And once we have this STL file, what we do is we prepare the data. We prepare the data because, as we have seen, the definition of additive manufacturing is it's a layer by layer manufacturing. That means, contrary to subtractive manufacturing, where we start cutting the material to get the desired shape, here we do not cut the material, but we lay the material. We deposit the material one layer at a time, then the second layer upon it, and we keep on depositing the layer in some using various principle, and in this way we get our thing done. So we need to get the information of each layer, that we call it as a slice. So here in this data preparation segment, we slice the model. Okay, so that we can get the details of each layer, and those details are sent to the machine, the 3D printer machine, which start depositing the material. If it is a case of an extrusion based 3D printing, so start depositing the material. But before we slice it, we select the orientation. Here you can see these tensile specimens, just two figures I have shown, where I have just shown that if I have to print this, I can print it in various orientation. I have just shown the two orientations here, and that means I can print it like this, laying flat, or I can print it at an inclined angle. At certain angle I can print it. So you can see the red portion over here is the support. So wherever there is an overhanging feature, this, after slicing, it is going to generate the support material. So when we print, we require those support material over there, and then we 3D print it. And once we have printed the part, we go for the post processing. Some techniques require post processing, some requires less compared to that. So if we have a support material, we need to remove the support material, and again the removal of the support material can be manual, or it can be a chemical based, where we just dissolve the support material, specifically when we talk about these extrusion based 3D printing processes. Okay, so this is a generic process flow about 3D printing. Okay, let's move forward, and we can classify them based on the just to refresh all your your memory regarding this thing. I have just in which the material is in the form of the discrete particle. We have material in the, one can classify them based on the material. Okay, so let's talk about more about the material aspect now. So if we talk about FDM process, fused deposition modeling, or fused filament fabrication, which is nowadays called as fused filament fabrication, the starting state of the material is in the filament. So we have a filament, a kind of a wire. Generally the diameter is 1.75 mm, and then we heat it. It is melted in the nozzle. So it is melted in the nozzle, and then we continuously start depositing it. We start continuously extrude it, and we deposit on the bed where we are printing. And the type of material that are generally used are thermoplastic, waxes, and nowadays we have a lot of composites which are available in the market also. When we talk about SLA, the material is in the form of liquid, which is resin in a vat, and we have a laser which scans. And this liquid is a photopolymer, which is UV curable resin. So on the exposure of these UV light, it start the polymerization process. And for SLS, SLM, 3DP, we have the material in the form of powder. So we have the material in the form of the powder. And then we have powder in the bed that we use, and then we use a laser to scan it. And here the materials can be, it can be thermoplastic, it can be metals, it can be polymers also. And when we talk about loam, the material in the form of a solid sheet, and we use a laser to cut the material, and then after cutting material one by one, we just try to stack them. So we feed the material, and we have a binding sheet, and we have adhesives. So in this way, what we do is we bind them, and the materials that can be used is paper, plastics, and even metals. They are used, but generally we won't find loam machines as much as compared to these FDM machines, but this is the technology that we use it. So we see that the material is in the different form, and different kind of materials can be processed by this. So, and we know that affects the application, it affects the dimension as well, the shape that we are getting, and the durability. So it affects it, or I should say it impacts, the material has a very crucial impact on the performance of the part that we are making. So they are kind of a building block in additive manufacturing. So the selection also of the material plays a very critical role for this end use application. And we have seen polymer, metal, ceramics, which can be processed, and we can also process the composites, like metal polymer composite, metal ceramic, polymer ceramic can be processed. And not only this, if we use it, the material in a nano scale, we can develop nano composites, and that can also be processed by 3D printing processes. And this can help us to enlarge the application domain of this technology, because now we can increase the desired properties, material properties of our part. So we can go with this. Now, why it is important? Just one example, that this is the, for example, if somebody is working on a project, if somebody have to develop a component which is used for, let's say, medical purposes, and so there are that it has to, this material should classify for certain certification. For example, if it's an instrument that has to be sterilized after every use, so it should have, I am making something which has to be biocompatible, then I have to select a material which is biocompatible. Okay, I have to look for FDA certification if required. Okay, fire retardant if I am using it for aerospace application. Okay, chemical resistance should be there. So there are so many things that one has to look when we select the material for any specific project, whether it's for medical purposes, whether it is for automobile or aerospace purposes. The certification has to be there specifically for aerospace and medical. So this is one example where there is a warping that is taking place of a polymer material, which is ABS, which has been 3D printed on autoclaving. Autoclaving is one of the technique of sterilization in medical industry. We go for autoclaving. That is, we try to sterilize the surface of our component, any the thing that we are using, the instrument that we are using, the equipment that we are using. And this autoclaving, it uses the steam at a certain pressure, but if use a material which is ABS, so there will be warpage. Okay, so I have to look also that after making the part, on what condition it has to be used. So so these are the very important thing at the time of selection, because I can make the instrument very easily. I can, this is material for extrusion based 3D printing, the polymer, so I can make it very easily. But after the application, when it has to be sterilized, it won't function properly, because it is going to be, there will be warpage. So the point over here is that selection of material is very, very important based on the application. So, and it affects the function that we have talked about. It affects the geometry, the post processing. There are so many things that comes into picture when we talk about the material selection. Okay, so now let's move and we talk about the technology specific material, how the selection of material plays an important role. What are the major, some of the materials that are present? So let's have a look on this. So we'll start with this fused filament fabrication, which is an extrusion based 3D printing process. And as you can see that generally we prefer amorphous thermoplastics. Generally we prefer amorphous thermoplastic are preferred. Okay, and this is due to their melt characteristics compared to the semi-crystalline polymers. So we also use semi-crystalline polymers. We use nylons and other polymers like PEEK also in extrusion-based 3D printing processes. But the thing that is preferred is the amorphous polymers, and there is a reason why we prefer this thing. So we'll just get into that. So this is what we prefer. Now what happens is, let me just give you one example. Over here, if you see on the right side, if you see the figure, it shows how the part is being built. That means the cross-sectional view of an fused filament fabricated part. It shows that. And in this thing, if we see that we deposit the one layer at a time and then the adjacent layer which are bonded together. And we can see, we can also, there will always be some voids over here. Okay, there always, so this is one of the inherent porosity of this property, I can say, of this technology. Okay, now coming back to why we prefer this, these amorphous plastics that we have, they have a broad temperature range. Okay, within which they can be softened, or you can say it can be converted to any other state of aggregation without any sudden alteration in their mechanical technological properties. So that is why the reason these amorphous are preferred. So we can see over here, but when we talk about semi-crystalline, so there is sharp change, there will be warpages and shrinkage problem associated when we go for printing this part, 3D printing part. So there is difficulty when we go for semi-crystalline material, use it for extrusion-based 3D printing because of the sudden cooling procedures that we have. But still we use it. We can manage it by providing proper setting, the bed temperature, the extruder temperature, even the environment temperature, if we can control. So that can be done. But the preference is given to the amorphous because these are much easier to process. Okay, so these are much easier to process. For example, ABS, this which is an amorphous, one of the widely used material. So let's move forward. So we have several thermoplastic materials which are used for fused filament fabrication. Like we have PLA, which material. Okay, we have different colors. PLA, but disadvantage, it's a little bit brittle more compared to the other processes that we have. Okay, which is widely used, high strength, flexibility. Okay, and important thing, extrude, so it is very easy to process. It is why it is widely used. Okay, but what it has, it is not issue of airborne microparticles. One of the issues which generally people do not bother, that should be taken care of. So there are certain airborne microparticles which are released into the atmosphere when we print these plastics. So one has to take care of this also. We have PC, we have nylon, and each one has their own advantages and their own disadvantages. Limitations are there. ABS. So these filaments are also available, and nowadays we are also getting the filament of polyether ketone, which is a very good material, but the temperature requirement for this material is much higher. It has application in aerospace industry, medical industry, in making polymer implants also. Grade, it can be used for making polymer implants, even in automobile it has its application. So very good material, good properties, but processing is difficult. We need machines which can go higher, let's say around 400 to 500 degrees Celsius. Other materials just require a maximum of 250 degrees Celsius. Okay, so these are some of the materials, and there are other materials also. Nowadays, if you'll find conductive material, composite filament are also there, like for example carbon fiber with ABS or PLA. We can find some conductive materials. So there are so many now filaments which are available commercially, and if one want to develop their own material or composite or a polymer blend, that is also welcome, because it is going to help to enlarge the application domain of this particular technology. Okay, now we have these flexible plastics also, which can be used in this scenario, which we call it as thermoplastic polyurethane TPU material, which is very flexible, and that can be used over here. And now, earlier processing of elastomers flexible material was very difficult because of the buckling that is going to take place. Whenever we want to extrude the material, the filament is pushed by the rollers and the mechanism that we have, then it is melted and it is extruded. So if there is no adequate stiffness in the filament itself, it is going to buckle and it is going to affect the extrusion process. So it was very difficult to process this, but now this material filaments of this, and this can be easily processed, and it provides a good elasticity also. So we can process very flexible parts with the help of this technology. And we can have this metallic filament as well. For example, this ultrafuse 316L is there. So this is the kind of a metal. It's not a entirely metallic filament, but it has polymer binders also. So we need to process it, and then we get a green part, and then we need to sinter the part so that we can dissolve this polymer binder out of it, and then we get a finished part which is a metallic part. Then we can go for post processing, we can set the dimensions out of it, and finally we get our part. So it does require a lot of post processing afterwards, because we need to sinter it. We get a green part, we need to sinter it, and then also we have to take care of the dimension, because after sintering the dimensions are going to be affected. So we provide that allowance at the time of designing of our part. So we provide the allowance at that part. So if we are using a metallic filament which has polymer and metals mixed into that, we have to keep in mind about the dimensions and the tolerance that we have to provide at the time of designing. Okay, let's move. These are few of the parameters that I just want to bring to your attentions. Like when we print a part, we first deposit the outer boundary, that we call it as a contour. After I can go for n numbers of contour. If I want, I can deposit only one outside boundary, or maybe two, or maybe three, and I can keep on increasing. It affects the performance of my part. It is going to affect the performance of my part. And then we have these raster angles. Okay, at which angle you're depositing the inside air gap, whether I want to give certain air gap or I want to put the air gap as 0. I want to get a 100% solid part, so I will make sure that the air gap is 0. Okay, so that is 100% infill density I want to give it. But again, even if we give 100, because this is what we said, this is an inherent porosity. inherent porosity, because the nozzle that we are using is circular in cross section, and when we deposit the semi molten material, it is deposited, and because of the cell weight we get an add one ellipse and adjacent to the other ellipse, and then make one layer, and then we deposit another layer, some gaps, because of the shape that we are getting. So this is the inherent porosity that we get in this particular thing. Okay, now this was about fused filament fabrication. That is about the extrusion based 3D printing process. Now let's talk about selective laser sintering, where we use a laser and we have a powder bed. Whether it is selective laser sintering or selective laser melting, the phenomenon remains almost the same, because we have a powder bed, whether it is of a polymer or a metal, and we use a laser. So how it works, let me give you this. We have these and these powder parts, the bed application of the laser, when it comes into contact with this, it transfer the heat of this sintering process that is taking neck, or which is taking place. When this necking in the figure, if you can see, if then when the neck
Vishal sir, hello, hello, hello. Dear participant, I think there is some technical glitch, so let me figure out. Okay, so just let me call to speaker. Dear participants, we are working on it. I think there is some technical issue with the sound, so our speaker is working on it. Okay, so once it rectify, then he will join us again. Thank you. Just be there.
Hello. Now I'm audible.
Yes, sir. You are audible now.
Okay, thank you, sir. Thank you.
I think sound is perfect.
Thank
I
you.
think.
Okay.
Now you can share your slide, sir.
Yeah,
Thank
sure,
you.
sir. Can you just tell me at what slide the voice was gone, so I can continue from there only.
Sir, please open your slide. Then I will tell you. First, please open a slide. Then I will tell you.
So this one, this is 26.
No, actually,
I
your
was there.
slides are not visible to us. So please share it again. Yeah. Okay. Yes. You are discussing this one, sir. Selective laser sintering,
Yeah.
SLS.
Yes. Yeah.
Okay.
So where we get disconnected at this point?
I think so. I can confirm with Miss audience.
Yeah. Your audience can just any participant can just
You
let me know.
write in the
So
chat box. Yes, we are getting. Miss. You
yes,
can
right.
put it in the chat.
Okay,
Yeah,
I think
one participant I think has confirmed. Yes.
here itself. Okay.
Okay. Yeah.
Okay. Thank you very much. Thank you. So we'll just start from here only. Thank you. Sorry for this technical problem. So here we were, and I was talking about we have a powder bed, and in the powder bed, what we generally have is the powder particles which are packed together, and we have in this figure it has been shown by a very you can say shape of powder particles, but in generally this size is going to vary. We all know that it is going to vary, but just for the sake of understanding, and on application of laser on to start taking place. So we have we start of this neck formation. We have a contact between this powder particles. This neck increase porosity is there, and this happens. Now in SLS, what we have is whenever we make one part, we use the remaining powder, certain degree of remaining powder, certain percentage of this powder, and we mix it with the fresh powder, and then we use it again. So this can be in different ratios depending upon the application that we are using. So the point is we recycle the powder that we have used. For example, I have a powder bed, I make a part, I take that part, but there is a remaining powder left. We take those remaining powder, we mix it with the fresh powder, and then we use it again. So here what we have, the selection of the temperature of my laser, and we also heat the powder bed, so to bring it at a certain degree. This is to be done at a proper range, otherwise there will be problem of agglomeration of particle itself. Before I use my laser, if the temperature of the bed itself is very high, the powder particle is going to agglomerate, they are going to connect with each other, and if this happens, it will increase the size of the particle, and if the size of the particle increases, what happens, the packing density will be affected, and if the packing density is affected, there will be porosities in my component, more porosity. So ultimately it is going to affect how my component is going to function. So the selection of parameter, ordinarily we have this sintering window. We have this heat technique, and this is the temperature range. This is the sintering we go for this thing. Okay, so this melting temperature is always higher than the crystallization temperature. So the setting of machine, the temperature should be between these two peaks, that is this melting and this crystalline temperature. Okay, so that the material which is melted by the laser, it remains in a particular temperature and in thermal equilibrium with the surrounding also, because I have to as well as the bottom one, so that not only intra bonding is there, but there is also interlayer bonding is also there. Okay, so these are the parameters which are very important in SLS, and some materials which are available, commercially available by some manufacturers, are these are polyamide with glass fiber. Polyamide, we have polycarbonate, SOMO, and so these are some of the materials which are available. Again, this is just to give you a glimpse of the material. Now we have a lot more of materials which are available, and one can also work on developing the materials. I'll just give you one example. Like, people have taken the polyamide material, this nylon particles, and they have coated it with each particle, they have coated it with carbon nanotubes, and then they have used it with this. In this way, they get a very good network of carbon nanotubes centered along with the powder particles, which enhances the electrical conducticity and so forth. So one can think of different ways of incorporating nano composite material, nano dimension material, and fillers, reinforcement we can provide to get the composites and nano composite out of it, and in this way we can actually enhance the properties of a material. Okay, so this will also tell us how it happens. So we have this grid which is and then when it's doing, it is also this penetrating inside to the previous layer, so that the previous layer also get bonded with this layer along with this thing. Okay, and we can see that this temperature about that so let's say this 6 was first layer, then the second layer. Now the laser is at this point number 2. It has moved, it's gone to 2, and now it is going to 1. So there is a thermal equilibrium is there, and we may sorry, and because of this, what we get is we get a good bonding between the particles, and we get a solid part out of it. So parameter selection is also important. And now if I select another material, then this thing, the temperature setting is going to change, because that has a different thermal characteristics. Okay, if I develop a composite, it will be having a different thermal characteristic. So I have to find out what is the temperature range in which I have to process that particular material, whether it's a composite or a new material. Let's talk about stereolithography apparatus. SLA have the material is in the form of a liquid. So it's sensitive polymer, and on the exposure of UV laser being the photopolymerization which takes place across, we have this formation of long chain is used, but it has a problem of warpage. It has a problem of warpage is in S. Are less prone to shrinkages, and um, technology. So what we have is, we have a photo initiator, and this, on the exposure of this UV light, it start reacting and it start forming chain monomer molecules M, and then this free radical, because of the presence of this free radical, we have this propagation of this chain and the cross linkages of this chain, and then finally the termination. So in this way, this liquid material is solidified, and we get this cross-linked polymer, and we just move our the stage upside, and then we get our part. We cure it to certain heat depending upon the material that we use. We cure it for required amount of time, and then we get our final part that can be used. So again, important parameters over here are the cure depth. So we can this is the depth, which is very important, because once I have made, this is the layer I am curing the layer, connect these two layer also, one layer with the other layer, then only I can get a solid part. So layer upon layer. So I have to make sure that not only to the this horizontal level I get that bonding, but also on the vertical side I get that bonding. That is, between the different layer also I get the bonding. Then only we can get this particular thing. As we have discussed, this extrusion-based fused filament fabrication was the first AM technique which has been used off the world, that is outside the world, because that's the 3D printer technology that we use in the space where we have zero gravity 3D printers installed. So it has very advantage, minimal wastage of materials, shorter lead time, and I can change the material very easily. Or a liquid resin, it's difficult to change, but if I have a polymer filament, I can change it very also there. And nowadays we have a lot of economical desktop printers. Okay, many people can do research, they can work it particular area. So these are some of the issues with this porosity and isotropy, because the properties that we get in XY direction is different than the properties that we get in Z direction. And there are problems of partial bonding, as we have seen. Porosity is always there, and we have very limited material. So because of this, what we get is, we get very low mechanical properties, we get inferior surface properties, and even no electrical properties. So one of the key is to overcome is the use of nanomaterials. Okay, the use of nanomaterials. So if I can use the nanomaterials wisely and properly, and develop some nano composite, so I can work on these there, or you can say the extrusion based process. Okay, so seeing the time, I'll just quickly go through these stages. I'll just show how this thing can be done, and then we'll take the question and answer round. So if I have to mix some nanomaterial with my printing media, there are few things that I have to look into. First is, what kind of disperse the nanoparticle within my printing media, and how these nano interacting with my printing media. If they're able to get a good nano composite, and I can get a good part. Now, this is to show that I can divide the stages of fused filament fabrication process into three major stages. First is, we prepare the filament, then we do the 3D printing process, and then we do the post processing. And these are very obvious three different stages if we take the overall picture of 3D printing. And if I want, I can add nanomaterial in the one. I can add nanomaterial in fabrication stage, that is a pre-processing stage, because still we have not done the 3D printing. So this is before 3D printing. I can add nanomaterials or any other material, whether it's a nanomaterial or a macro level material, micro level material. I can also add it at that time during 3D printing process. I can also after 3D printing process, which is the post process. So I can add in these three different materials in these three different stages. Different kind of dispersion will be there, and the interaction between the nanomaterial and the printing media will be different. So I do this by introducing nanomaterials in different stages, and because of this I will get different kind of properties which one can tailor as per the need, and then they can use it as per their application. So this is a glimpse of some of the people which have done this at a pre-processing stage, that is before the 3D print nanomaterial, during the 3D printing, and some people have processing, that is after the 3D printing process. But still, those who have used it after the 3D printing process, they are not the nanomaterials. Okay, so but I'll just show you these three different stages one by one quickly, so that we can just finish it in 10 minutes. So the first stage, that is if I want to add nanomaterials into this stage right there. So when I can do this, I can get a reinforcement in my filament itself. So the filament I am making, which is nanocomposite, so the filament itself is the stronger one if I'm focusing on a mechanical aspect. So it's if I'm focusing on if I want to use it for some electrical component, then I'll focus it so that it is conductive material or maybe a dielectric material as per the requirement. So we make a filament itself as per the requirement. If I want mechanical strength, I will mix it with the nanomaterials or the fillers which will improve the mechanical strength. Okay, so we can this is the one of the strategy that one can use to prepare these things, prepare a master batch, use a filament fabric. One can go for the 3D printing. And when we go this, these are some of the proofs where we have seen the improvement in the thermal as well as in the mechanical aspect. So depending upon how much weight percent we are introducing, it is going to affect whether we are going to improve the tensile strength or the Young's modulus. So one can improve these properties. Okay, so and we can go for different characterization techniques to check whether our the composite that we have made it's the good one or not, whether we were able to disperse it properly or not, whether there is exploitation of our particles or not. In this way one can go for this, and we can improve the properties. Okay, so we can provide, for example, in this case I have used the nano clay with ABS, and we have seen that the properties have been increased, the mechanical properties. So this is where we have introduced the nanoparticles, nanomaterial at the time of filament fabrication itself. And once we have that nano composite filament, that we have used to make the part. Okay, so these are the few of the techniques. The time doesn't give us permission to go in detail, but this is the second one which I want. If I want to add nanomaterial at this stage, at the time of 3D printing, so again I can go for this fused filament fabrication process. It over here. strategy that one can use is, let me show you the strategy one can use it. We have this as a material. So I have a filament, I have just coated it with the nano material. And then when I use that material to make, prepare the filament to go for 3D printing, what is going to happen? When it is heated and extruded, this coating fuses with the inside. Yes, this is the grayish is the inside core of one, yellow one is the coating only. So when we heat it and extrude it, this coating mixes with the inside part, and we get something like a fused network of polymer and layer silicate. We get something like this. So this is the strategy that one can use. We coat it properly. You can see we coat it, and then we print it. We'll get something like this, the structure. And if you see this particle which has intercalated with the polymer chain at the boundary. Okay, so this is the point. It is only at the boundary here. It is not get in elliptical shape which illustrates the raster boundaries over here. And this helps us not to increase the mechanical properties, but it helps us to increase the dielectric properties compared to this. So when we do this analysis, we found out the mechanical properties were not much affected by this, but the dielectric properties were much more affected. So the dielectric properties were because of the polarization of this host polymer molecules and the clay particles which are negatively charged. This provided a lot of polarization, and so we found that the dielectric properties were introduced. So one can tailor these dielectric properties. So I can, you can see that gray represent ABS, this represent nanocomposite. Make different patterns. I can tailor the amount of dielectric properties that I want in my various applications. So one can work on that also. This is also very interesting thing. And last, not the least, is the last one where we provide this nanocomposite at the third stage, that is processing stage. I can provide it over here. And then you can see that the surface will be affected because it's just the post-process. I cannot get inside it, but the surface can be affected. So this is the schematic, how we have gone through this. We have first printed the part, then we have immersed it in nanoparticles are embedded on the surface only. We can see this. And if we wisely select the chemical, these to be getting. But if we use this polymer, and we select the parameters, that is the time required to that is in contact between the polymer and the chemical, we can get a smoother finish. We can get a much smoother finish. So these are some of the results which shows that how one can increase the surface properties. So surface hardness can be increased, and surface roughness was reduced to a greater extent, you can see. And these are some of the images which shows the reduction in the surface roughness. Okay, and also the dimension have to be kept in mind, obviously, because when we go for post processing and we are doing some chemical operation over at along with the nanoparticles, then the dimension will be affected. So we have to take care of the dimension as well. Okay, so in short, let me just quickly summarize this. So we have 3 stages, basic stages, and in these 3 stages, one can add nanomaterials. One can add nanomaterials in different ways, and we'll get different properties. So I can add it in pre-processing, on stage, and in this way. So it's pre-processing, on stage, or post-processing stage. I can add these things. And we get different, interaction. These are the proofs of interaction that we get between different techniques. And because of this, we are getting different properties. If I want let me just show you this. If I want a major property incorporation, improve my mechanical strength, I will add the nanoparticle in the first stage, that is filament fabrication. This is specifically for when we use clay particles. If you use some other, you may get different result, but majorly it will be something like this. If you add at the time of nanoparticles, we get improved dielectric properties, and when we add nanoparticles at the post-processing, we get improved surface properties. So in this way, we can just play around with this. At what stage we are improving the nanoparticles, we can get different kind of interaction and hence the different properties. So not only the materials which are available to us, we can also take them and use them, and if we want to develop a specific material for a specific application, we can work on that as well. Okay, so I think the time limit has been done, so I'll just stop over here. Okay, so just give me 1 second. I'll just stop over here. Okay, Dr. Naren is here. If we can open for okay, so I have some queries regarding the presentation. Sure, I'll share with Dr. Naren and he can provide it with you all. Yes. Coating thickness is very important. Very good question. This thing is, if I am taking a filament, predetermined filament, for example, then generally the diameter of that filament is 1.75 mm, and this is the diameter which generally our machines take. So the machine that I have used was a flash forge one, and in that the maximum thickness that I can go was around 1.9. So I have to make sure that the thickness do not increases more than 1.9, otherwise it will be blocking my way. And once I change the thickness, the output, the throughput of the nozzle is also going to be affected. For space applications, we have different materials. One of the material developed by Stratasys is Ultem. Is great material which can be used for aerospace. So for aerospace, I have to make that that particular material is certified. Yes, so it has to be certified. Thank you. Okay, yeah. Any other questions? You can proceed. So because of the time, I have to wrap up the last section of the part quickly. So please bear with me.
But sir, I think your slides are not visible, sir. I think.
Sir, we have just finished the slide. Yes, we just finished the slide, and we just into question answer round. So.
Okay. So participants, if you want to ask any query to our speaker, then you can raise your hand. So I will switch on your mic.
Okay. So some have asked question in the chat box, sir.
I have seen. But still, if you want to ask.
Yes, sure.
Then I can take some queries directly from the participants. So I think one of the participants, Dr. P. Prabhakar Rao, I think he wants to to ask some question to our speaker. So I am making him presenter. So Prabhakar sir, now you can ask.
Yes, sir. Good morning, sir. It was a nice presentation. I would like to ask Vishal Francis, sir. It's a nice and informative presentation. I would like to know from you, as you know, during SLS process, once the powder is sintered, now is there any shrinking round? Means, as you know, in case of powder form, whenever it is bonded, the neck is formed and this what you call the grain boundaries are formed. Now at that time the shrink size is increasing, and now there will be what you call a sudden shrink. Then how these can be addressed, sir?
Okay,
In
sir.
any
Yeah. Thank you, sir. Thank you, sir, for the question. When we got SLS, where we have the powder bed of the polymer, we also heat the bed. Heat the bed itself. We put it at a particular temperature, and the to maintain is between that centering window that we have. So this keep the the temperature of our these particles within this equilibrium. So the sudden cooling thing doesn't happen that much, and it does not affect that much to that thing.
Okay. Okay,
Yeah.
sir. Thank you.
Thank you, sir. Thank you. One more question is there for Santosh. Sir has asked. For nowadays we have filament in which we put some metal particles inside the polymer filament. So we have one example I have given, that is we have that 316L stainless steel, which is mixed with the polymer binder, and we have the filament. So it is not coated, it is actually mixed inside that particular thing. But if we want to go for coating it, then one has to look for one thing, that we have to keep the nozzle, that we want to get it into a stainless steel nozzle first. Otherwise it will there will be issues with the extrusion process itself, and we have to take care of the thickness of the filament itself. However, coating has been done with the clay. I have done some people, there was one project of NASA where people have done use carbon nanotube as a coating also. Okay. Clay can be used. I have used nano clay, so I can say nano clay can be used. The temperature does not requirement does not exceed very much. So if my machine is of 250 degrees Celsius maximum temperature, I can process it. But if I use some other base material like PEEK and other thing, so the temperature requirement of those material itself is very high. So I cannot use those machines. I have to use machines which can go higher at around 500 degrees Celsius. Can we use natural fiber? Yes, we can use natural fiber also. People have worked on this and natural fiber. Also synthetic fiber like carbon fiber also people are using nowadays. Natural fiber we can also use. The reason is that triangular meshing, it makes the slicing procedure very easy. One of the reason is it makes the slicing procedure very easy.
Sir, I think some more queries from our participant.
Yes.
Subramaniam, I think he has already, written his query in the chat box. So I'm not taking his query now. So I think participant, no query from your side. So thank you, Dr. Vishal, for sharing your knowledge with us. And thank you for accepting our invitation and sparing some your valuable time with us. I hope the knowledge will be utilized by our participants in future, and they will be benefited. Thank you very much,
sir. Thank you, sir. I've just given my email. If somebody has queries, you can just write a mail.
Okay. I will convey your message to through WhatsApp group.
Okay, yes, sir. Sure. Thank you, sir, very much. Thank you, sir.
Okay, thank you very much, sir.
Thank you, sir.
Thank you.
As per you, our next speaker is Dr. Narendra Kumar. He is the coordinator, or you can say the organizer of this program. So before inviting to Dr. Narendra Kumar, I would like to give some brief introduction of Dr. Narendra. He is an assistant professor in the Department of Industrial and Production Engineering at NIT Jalandhar. He obtained his PhD degree in mechanical engineering from IIIT Jabalpur. His research work is based on development and performance evaluation of pellet-based additive manufacturing process for flexible parts. And his thesis project was also the part of DST-sponsored project, which was hybrid additive subtractive manufacturing system using CNC Machine Center. Prior to joining the NIT Jalandhar, Dr. Narendra has also worked in Bajaj Institute of Technology, Varda, and he has also worked on the different projects of DST, like development of metal-based deposition system using induction heating method as a research associate. He has also worked on some different platform. As an research interest, is broadly related to the additive manufacturing, machining methods, and material development, and so many more. Dr. Narendra has also published around 35 research papers in the International Journal and Conference Proceeding of High Repute, and also edited 3 books of Springer. So with these words, I would like to invite Dr. Narendra to deliver his talk on 3D printing. Dr. Narendra, you can start now.
Thank you, Dr. Moityagi, for introduction. So dear participants, I welcome you all in this talk. So now let me share my PPT with you, then I'll start my talk. And I hope my presentation is visible to all. So can you write in the chat box if my presentation is visible to all? Then please. Okay, fine. Thank you. Thank you very much. So dear participants, today I am going to discuss about the recent trends and some advances in the area of additive manufacturing. And then I think, let me check. I think some. Okay, so so in today lecture I am going to discuss about the some trends which are currently going on in the area of additive manufacturing, and then I will discuss some of the case studies. Okay. So these are my presentation outlines. So first I am going to cover about the additive manufacturing. Okay, and in short I will tell you about additive manufacturing, and then I will discuss about the recent trends in the different domains, right? And then challenges. What are the challenges means we are facing in the area of additive manufacturing? Then I will means discuss some case studies, and then some other research works are also there. So those I would have to discuss with you. So what is additive manufacturing? How it is different from the other manufacturing processes? So according to the ASTM F40 committee, so the additive manufacturing. Participant, I think there is some. Let me work out on that. I think there is some disturbance. Let me check. Okay, so according to the ASTM F42, the additive manufacturing is a process of joining different materials to make objects from 3D model data, and that is usually added in the layer upon layer manner. Okay, so how we start means this additive manufacturing. First we take 3D model data, and then we slice it, then we go for toolpath generation, then we go for actual manufacturing. Okay, so it is just opposite to the subtractive manufacturing processes, right? because here we are adding the material in layer by layer manner. But in subtractive manufacturing, we have to remove the material in the form of chips from the stock. Okay, so we can say it is a digital fabrication, right? And it takes a model, okay, and it consider a digital design which we can prepare in any of the software. Then we can turn that design into the real or physical object. Okay, so in this figure you can see how the material is being added, okay, and how the all layers are deposited from the nozzle, and in order to get a three-dimensional object. So this particular topic or slide has already been discussed by the other speakers. Okay, so let me revise it again. So that is process chain of additive manufacturing. So you can see the CAD model. So first we have CAD model, then we tessellated that particular model which we have already prepared in the software, and then we go for slicing, and then we go for toolpath generation, then we go for part fabrication, then post processing. So CAD model you can prepare in the software, or you can download it, because nowadays what is happening nowadays the various websites are available on which you can find the different CAD models, okay, which may be used by you. So as per your requirement, as per your use, you can download any model from there. So I remember one of the website, that is thingiverse.com. Okay, so where you can find the models of different objects, right? So you can download them directly from there, and then you can print them. So tessellation. So I think one of the participants in the last session asked about the tessellation. Means why we consider triangulation, why we are not considering any higher order polygon, okay, in order to do the tessellation. So the answer is that because triangle is the smallest polygon, okay. So we can if suppose if we have curvature, means in the object, so we can easily approximate that particular curved surface with the triangle easily. Okay, and another benefit with the triangle is that because triangle has 3 linear segments. Okay, so we can easily find out the intersection between plane and line. So in this manner, the slicing procedure is bit easier. Okay, so if we go for higher order polygons or other polygons, then we will face many difficulties, and it is very difficult to get the contour information. So that's why we prefer triangles for the tessellation purpose. And then slicing. Okay, slicing is nothing but the extraction of the contour information at various Z heights, because we are going to add different different layers together at various Z heights, okay, at various heights. So here in the slicing, what we do, we extract contour information. For example, let me take one example here. Suppose here I am having a cylinder, right? So this is suppose this is a CAD model of a cylinder, right? And now I am going to slice it. How I can make this cylinder through additive manufacturing? If I add multiple layers in this direction, okay, if this is oriental, then I have to add different layers. So each layer will have circular cross section. Okay, so this circular cross section information is required in order to fill this layer. So in the slicing, we extract this information. Okay, so this information is extracted at various Z height. So this is our Z or height of this particular object. So we will extract the contour information along the Z direction only. So that is basically known as slicing. Then we have toolpath generation. So now we have contour with us. Okay, suppose this is contour. Now, in order to make this layer, or in order to make this particular layer, we have to fill the area inside the contour. So how can I fill it? I have to choose some particular toolpath in order to fill this. So I can fill it like this. So this is known as basically raster. Okay, so this is raster one. So through this toolpath, I can easily get or easily fill this particular layer. Okay, so toolpath generation is another important step. Then we go for part fabrication. So we load this data on the machine and then we fabricate three-dimensional objects, right? Then sometimes post processing is required, and the post processing depends on the various factors. Factor means what kind of support structure you have used in your during the part fabrication, right? And have you used raft, or have you used any support structure for the base of that particular object? So it depends on various factors. Okay, and based on that you can choose any technique for post processing. Okay, sometimes you want good surface finish, but if you look into the look at the 3D printed parts, then the surface finish of those parts is not that much good. So you can go for the improvement of the surface finish, surface roughness. So you can improve that. So in order to improve the surface roughness of that particular object, we can choose the different techniques. So that is again comes in the category of post processing. Okay. So post processing depend on the various factors, and what kind of post processing technique you are going to choose, it will also depend on the various factors, right? Now the question is, what are the different research areas where the researchers are working on? Means what are the different research domain in which, if you are a young researcher, okay, then what are the different domains in which you can proceed further? So I will discuss one by one each step. Okay. So CAD model actually it depends on your requirement. Okay. So I cannot suggest any research here. Okay, at this during the CAD modeling, but I can suggest some of the research topic during the tessellation and what can you done. Okay, so if I talk about the tessellation, then you know STL is one of the file format which is generally used by the researchers or by the other users of 3D printing. Okay, but STL, if you go into the detail, then you will find lot of problems with the STL file. So we have some more lectures on STL. Okay, so in which some other speakers are going to discuss about the STL and other and the issues related to the STL files. So you can go into the detail, and then you can find the different issues with the STL file. Then you can propose some new topic, or you can propose a new file format. Other than STL, you can propose a new file format, okay, which will overcome the issues of the STL file. So here this can be a good research area as of as by considering the current situation of additive manufacturing, because we are lacking here we are not having sufficient file formats. Okay, so STL has become a de facto standard, and people are using still there are some problem with STL, but still people are using STL file format in the additive manufacturing. Okay, so this can be a new research area. Means you can propose a new file format, okay, that can overcome the issues of STL file, right? Then slicing. So slicing, if you search some research paper in the slicing direction, then you will find there are two types of slicing processes. One is the uniform slicing, and second is the adaptive slicing. So still the research is very limited in this area. So you can search, you can go into the detail, and you can search about slicing, and you can see the benefit with adaptive slicing, and where we can use adaptive slicing or where we can use uniform slicing. Uniform slicing means we are giving uniform gap between the different layers. Okay, Adaptive slicing means the size of the different layers will be different. Okay, so where it is applicable, you have to find out, and accordingly you can select means this as a research topic. And again, another means research area where you can do slicing directly from the CAD model. This is also in the trend. You can skip this one, this tessellation, right? And how can do it? Like suppose I have point cloud data of a CAD model, then I can use those points in order to do the slicing operation. So I can jump directly from CAD modeling to slicing. So this is another topic. Here you can propose some of the algorithms in which you can discuss like direct slicing of the CAD models. So this is another research area. Okay. So here I am skipping this particular stage, tessellation. Means I am not going for tessellation. What I am going to do, I am just skipping this step, and then I am directly jumping to the slicing from the CAD modeling. So this can be another research area where you can start your research work. Okay, you can think about it. How can we how can we extract the contour information directly from the CAD model? Okay, and then toolpath generation. So toolpath generation means, so as I told you, suppose if I am having a contour, okay, I have taken this example, this particular example. So you can see, suppose I am having this contour information with me. So toolpath generation, how can it be considered as the research area? So here I can explore the different toolpaths or toolpath patterns. So one pattern I have already suggested you, that raster pattern, that is very popular, okay, among the researchers and among the the users of 3D printing. But there are various toolpath patterns available. Okay, like how can I fill it? I can fill it by offsetting approach. Okay, suppose I am having this contour, I can fill it by just offsetting technique. So each time I am offsetting my contour and I am just moving towards the center. Okay, so in this manner I can easily fill out the area of this particular contour. Okay, and then some other type of patterns like fractal pattern is there. Okay, so you can find one of my research paper in this on the fractal toolpath. So fractal toolpath means, if you see means this particular raster pattern, then what is happening? Suppose I am having a layer, sorry, I am having a this layered information. Okay, I am having this slice. So suppose my nozzle is here and it is depositing material in order to fill this particular layer. Okay, so just consider, because I am not having pen, I am using this layer. Let me. Okay, how the fractal can be useful in 3D printing. So just I want to tell you about the fractal toolpath. So suppose now my nozzle is coming back. Okay, so initially my nozzle was going toward this direction, and then it is coming back to this direction. So what will happen if you pick 2 points, means one point here and second point is here, then what will happen? There will be huge difference between the temperature, because almost there is a lot of time here, means lot of time is actually taken by the nozzle, because nozzle was moving this side and then again it is coming to this side. So if you consider the time, then you have to check the temperature between these 2 points, then you will find the temperature difference. Okay, so the large temperature gradient will be there. So in that case, the bonding between these two particular rasters or rods will be very poor. So what you can do, you can propose some new toolpaths in this area, right? All right, so this is means one of the benefit with the fractal toolpath. So fractal means this is pattern, like this is a pattern. Okay, so this kind of pattern actually we use. Sorry for this kind of drawing, very poor drawing is here. Okay, because I am not having the pen, I am using the, let me. Okay, so some other toolpath can be explored in order to get the good bonding between the rasters and between the layers. So this particular step you can consider as one of the research area, right? Then you can go for part fabrication, and the part fabrication will depend on the factors which you have considered during the previous steps. Then post processing. This is again a very important research domain in which you can where you can start your research work. So post processing means you can apply some chemical based techniques in order to get the good surface finish, okay, and also you can apply some techniques in order to get the good bonding between the rasters. So like in the previous lecture, Dr. Vishal Francis has discussed about the clay addition, okay, so he has discussed about the different stages. So different stages of clay addition, and he has shown the benefit of clay, okay. So one of the stage is the post processing, means after part fabrication we can add clay on the surface of the parts, or else we can go for some other techniques by which we can improve the bonding between the rasters and between the layers. So this can be the another research area where you will find a lot of research papers. Also you can start your research work in this area too. Okay. So so what are the different techniques of additive manufacturing? What are the different techniques available with us? So here I have taken the classification based on the principle, working principle. So first is the material extrusion. So material extrusion means here we will extrude the material in the viscous form on the bed, okay. So FDM is one of the process. Another name as I told you that is triple F, okay. So triple F is the another name, okay. The working principle is quite similar. Only difference is that triple F basically people are considering as the open source, okay, and FDM is actually the proprietary name of the statistic. So that's why people are not using FDM. So instead of FDM they are using triple F, okay. And second principle is the wet polymerization. So in which we use the resin in the liquid form, okay, and then we prepare or we make three-dimensional object from the liquid type of material. So in which there are two processes, SLA and DLP, okay. And then we have another type of additive manufacturing techniques, that is powder bed fusion. So one is for polymer and second is for metals. So for polymer we have one process, that is selective laser sintering, SLS. Then another next classification is the material jetting. So material jetting means here we will use the jet of material. So material will be in the liquid form, and then we will inject this material on the bed, okay. So here we have two processes, and that one is the first is the material jetting, and second is the demand on drop on demand, DOD, okay. Then the next classification is the binder jetting. So here we have one process, that is binder jetting, okay. So here we will use the binder, okay. So binder means we can bind the sand particles, okay, together by using this particular process. So I will discuss some of the trends or what is actually going on in these different type of additive manufacturing techniques, okay. So I will discuss with you about this, okay. Then powder bed fusion for metals, in which we are having the direct metal laser sintering, DMLS, and then sectorial melting, then EVM. So this is new process, basically EVM, electron beam melting. So I will show you the current trends in this area, okay. But before I go into the detail, I would discuss about the principle, means how these different techniques actually work, and how can we make a three-dimensional object by using these different principles, right? So first is the wet photopolymerization. So actually these processes utilize a liquid photopolymer. Okay, so here the material will be in the liquid form, and that is contained in a vat. So vat basically is a storage kind of thing. Okay, so in which we store this liquid photopolymer, and then we process this particular region by selectively delivering energy to cure specific regions. Okay, so we will be selectively. What is the meaning of selectively delivering energy? So here we will have energy source or the heating source. Okay, so that will be used selectively, means on the selective region we will switch on this particular energy source, and then we will cure that particular region only. Right. So based on the layer information, based on the slicing information, the selective region will be the specific region will be selected, and then that particular region will be cured. Okay. Then second is the powder bed fusion. So powder bed fusion basically it processes the so here instead of the liquid, the container will be filled with the powder material. Okay. So in the previous method we were using the liquid photopolymer, but here we use powder particles, and those powder particles are processed selectively. So again the selective means the principle is quite similar, right? But in the wet photopolymerization we use photopolymers. Okay, so those photopolymers actually cure when they are exposed to the some particular energy source. Okay, and here these powder particles actually they fuse together. Okay, they actually bunch together when we use a laser beam. Okay, so when we selectively pass the laser beam on the powder particles as an energy source, then the powder particles actually fuse together, right? And then we have material extrusion. So this is actually very popular. I think you all know about the FDM and AAA process. So material extrusion is the principle on which these machines actually work. Okay, so this is the process that deposit a material by extruding it through a nozzle. So here we used different sizes of nozzle. Okay, so you can select the size of the nozzle based on your requirement. So generally people are using the nozzle with 0.4 mm size, right? So and different patterns can be used to deposit material on the build platform, and be generally means the printers are coming with the open architecture and the closed architecture. So I will show you later on what is the meaning of open architecture and the closed architecture. Okay, so and then next is the material jetting. So the principle is quite similar to the inkjet printing process. So inkjet printing process means like we take print out on the papers. Okay, so where we use ink, right? So people have developed basically this kind of process. Okay, so instead of paper printing, now they are using the same principle for 3-dimensional part printing. So instead of the ink, we inject resin. So resin is injected at the place of ink. So we use this principle in order to make 3-dimensional objects. Then we have another process or another category, that is binder jetting. So these processes where a binder is deposited into a powder bed. So again here we use powder particles, okay, as the raw material, and how we bind them in the SLS or in the powder bed fusion. What we were doing here, we were using the laser in order to bind the powder particles together. But here what we are doing, we are using a binder. Okay, so this binder will be deposited on the powder bed. So powder bed means where the powder particles already spreaded. Okay, so where we will deposit this binder, and then we will form the 3-dimensional objects. So with this technique, sand printing is also possible. I will tell you the company name who is manufacturing this particular sand printer. Okay. So sand printing means sand particles can be easily binded, okay, by using the binder materials. So binder is deposited on the powder bed, and then we can have the three-dimensional objects. Then now next process is the sheet lamination. So sheet lamination, one of the process I know which work on this principle, that is laminated object manufacturing, LOM. So this sheet lamination processes actually they do not deposit a layer of material. Basically, we use a paper type of material. So initially we keep the paper material on the build platform, okay, and then we use a laser beam to cut the cross sectional. Actually the laser beam will be passed through the contour. Contour means along the periphery of the contour, okay. Then paper will be burn out, and we will have a layer, right? So laminated object manufacturing is a process which work on this principle, sheet lamination. But nowadays this particular process has been obsoleted, and people are not using this particular process to okay, because we have some other processes, okay, which are better than this particular one, okay. Then another category we have directed energy deposition. So this is nowadays it is in the trend, because our requirement are nowadays actually our requirements are different. Means we want strength within the part, okay, and also we want to print metallic materials, and also build time should be less. So there means a lot of requirements. So that's why people actually have came up with this particular principle, okay, where they are using the directed energy deposition principle. So I will tell you how we can use it for 3D printing. So so these particular processes simultaneously deposit a material, okay. So material may be in the form of powder or in the form of wire, okay, and then the energy is provided to process that material through a single deposition device. So here I know two process: lens laminated lens laser engine net shaping, and second is the EBAM, electron beam additive manufacturing. So there are two processes in this category which are using this directed energy deposition principle. Sorry. So now what are the key developments in the different domains of 3D printing? Means what are the key developments in the wet photopolymerization, and what are the key developments in the area of powder bed fusion, what are the key developments in the area of material extrusion. So here we will discuss those developments one by one. So first I am going to discuss about the key developments in the wet photopolymerization. So as I told you, the liquid photopolymer in a wet is selectively cured by light activated photopolymerization, okay. So I have already discussed the principle of this. So you can see here so here we are using a light, okay, light source, okay, and here we are having a wet, okay, and the material is selectively cured. So material is nothing but liquid photopolymer. So you can find you can search the videos of this particular process, okay. You can search for internet stereolithography. So this was the first additive manufacturing process that was developed long back in around 1987. So people actually used to fabricate their part by using SLA process, okay, for prototyping. So what are the key developments in this area? So first is the expiration of initial stereolithography patents are opening up the marketplace, because it was developed long back. Okay, so all the patents are now expired. So you can we see some new printers in this area, or is based on this principle in near future. So they will be less costly, okay, and they will be available means with open source software, right? My screen is visible to all. Hello. Let me check. I think one message actually I got. Yeah, visual. Okay, okay. Actually, I got one message from Sachin Nagure. He is saying no screen visible, but I think it is visible to all. Okay. Thank you. Thank you for confirming. Okay, so here means what is happening in the area of wet photopolymerization. All the patents are now expiring, okay, or getting expired. So people are coming up with new ideas. So due to this expiration of patents, the number of 3D printers are coming, okay, based on this principle, okay. But now people have used the different means energy source. So what they are doing, they are using projector based techniques, okay. So what is the benefit with this projector based technique? The entire layer can be cured at a time, because with the laser, what was the problem? We were selectively choosing the region, okay, and we were supposed to use the raster pattern or any other pattern, okay. So it was taking a lot of time, but with new techniques we can cure the entire layer at a time. So at once we can switch on the light source, and then whole entire layer can be cured. This is one of the benefit with the new type of 3D printers, okay. So people are coming up with the new ideas, okay, and you can search on internet DLP printer. So you can find this printer for 40,000 rupees or 50,000 rupees. So there is range, okay, between 30 and 50,000 in which you can find these printers, okay. So now you can compare the cost. Means the previously the SLA cost was very high, right? The price was too high for the consumer, but nowadays, because all the patents have expired, and now people have started developing new kind of 3D printers. So they are cost effective in nature, and also the consumer can think about customer can purchase them, okay. And in the near future you will see this particular range will be decreased. You will be able to purchase SLA printer or this photo the printer with this technique. You can find them easily. You will be able to find them for 20,000 rupees only, like the things are happening with the FDM or the triple F, okay. Then key developments in the area of material extrusion. So material extrusion, material is selectively dispensed from the nozzle or the orifice, okay. So a small nozzle is there, we use, as I told you. So different sizes of the nozzle can be considered for the part fabrication. So what is the principle? As I told you, we use the material in the filament form. So feed roller is there, right? Liquefier is there, and then we are having a nozzle, and by using this nozzle we extrude the material in the form of wire, and then we deposit that material on the build platform in order to get the three-dimensional object. So what are the current developments? What are the key developments in this area? So this is one of the in this area, that is the expiration of patents. So patents have been expired now, okay. So all the patents related to the FDM actually were expired in 2007. Okay, so after 2007, people have started developing or have started means understanding about this technology, and they started manufacturing of the small 3D printers based on this technology. So nowadays, what is happening means more personal 3D printers are being sold in the market for just rupees 15,000 and 20,000 rupees. Okay, and if you directly buy from China or the other countries, okay, who are manufacturing the 3D printers, if you approach them, then you will be able to get this printer only for 10,000 or 8,000 or 9,000 rupees. Okay, and also the industrial printers are also available for 5 lakh to 500 lakh. So there is huge range there. Okay, but personal machines are very cost effective. I think in every institute we are having 3D printers. Okay, so they are based on this technique, material extrusion. So 400 plus manufacturers are there who are manufacturing the printers or the machines based on the material extrusion principle. Okay, so due to this cost effectiveness of this technology, people are taking interest in this technique, and they are trying to make their part by extrusion technique. Okay, and nowadays the focus actually is shifting toward the high temperature material, because currently we are having material like ABS, PLA, nylon. Okay, so if you check the melting point or the melting point of these materials, so it is around it is about the 250 or 260 degrees centigrade. Okay, now people are focusing on the high temperature material, right? So they are trying to explore some new materials, and they're trying to explore some composite materials. Even though people are using this particular technique, extrusion technique, to print the concrete to extrude the concrete materials, even though people are using these technique in order to make a home. So 3D printed home, you can search on internet, then you will find a lot of videos. Okay, so where people are using the concrete based materials. Okay, so they are extruding from the nozzle. Okay, and then they are making balls, they are making roofs, they are making different structures. So this is one of the benefit, because this technique is very useful and very popular. Okay, and one more thing which is happening in this domain, that is big area additive manufacturing. Big area means the large size part fabrication is also being explored by the researchers. So one of the laboratory I know, that is the Oak Ridge National Laboratory, ORNL. So actually they are focusing on the big area additive manufacturing. So they are abbreviating this particular process as the BAM, BAAM, big area additive manufacturing. So focus means you can also consider this as a research topic. If you are a MTech student or PhD student, okay, and if you are looking toward the research topic, then this can be one of the research area where you can enter. Okay, so that is big area. So you can develop your own 3D printer with the large size of nozzles or with large size of component. Okay, then you can try to fabricate large size of parts. So this is this is the So next is the key developments in the powder bed fusion. Key developments in the powder bed fusion. So powder bed fusion basically, as I told you, in which we use powder materials. Okay, so it is the most used platform for functional part. So if you want to make the functional part, then we can go with the powder bed fusion. Why? Because what is the problem with material extrusion? Because surface finish and dimension accuracy of the material extrusion of the material extrusion technique is not that much good. because here the powder particle size is very smaller, okay, very small. So in this case we can get we can fabricate parts with good dimension accuracy and the good surface finish. So that's why, due to these features, it is the most used platform for functional part fabrication. Okay, and people also doing research. Okay, they are investing a lot of money in this on this not particular domain. Why, I will tell you later on. So many metal machine manufacturer actually have come up with their machines like RCAM, SLM solution, concept lasers, EOS, 3D system, Phoenix, Reniso. So I think you might have heard about the Reniso. It is very popular, and also 3D system and EOS. So these are the three manufacturers means who are very popular in this area, and they are manufacturing metal based 3D printers. Okay, so metal based machines actually are being manufactured by these. So you can see number of manufacturers are entering in this area. Okay, and in future we will see many more will also enter. So many new metal laser sintering machines are coming up. So additive industries, Metrofab, Bello 3D, Japanese and Chinese manufacturing industries. So they are coming up with the new metal laser sintering techniques. Sintering machines. Okay. So all these machines actually are based on this powder bed fusion principle. Because that nowadays demand means people are demanding of the metal products, right? Means the additive manufacturing nowadays not limited to the prototyping. Means we can make functional parts. So functional parts should have sufficient strength. Then only it can be used for the means for in some particular application. That's why people are focusing on the metal based additive manufacturing or the metal based 3D printing. So that's why many companies are coming up with their machines. They have different specifications, but almost principles working principle is similar. Okay, they all are working on the powder bed fusion. Okay. And also in future we will see a new polymer machine manufacturer. Nowadays only very limited manufacturers are there, and in future also we will see the battle between open versus closed machine architecture machines. What is the difference open and closed? So I think you have seen in the case of metal extrusion printers, like if you I don't know if you have see any 3D printer or any FFF based 3D printer, then there will be two type of architecture. First is the open one. Okay, so printers basically you will get around for 15,000 or 20,000 rupees. They will have the open architecture. Only 3-axis system will be there, nozzle will be there only. Okay, but if you go for 2 lakh or 3 lakh rupees machine, then they have the closed architecture. So they will be closed from the all side, and also temperature environment can be controlled easily. So temperature sensors will be there, and temperature heaters will be there. So a lot of things actually will be installed when we try to make a closed machine architecture. Okay, or a closed machine with these features. Okay, so here in the future we will see the battle between open and the closed machine architectures. Okay. Then what are the key developments in the material jetting? So as I told you, the droplets of build material are selectively deposited, right? So if you want to make, so you can see here we are having a jetting head, right? Then we are having UV light. Okay, so it will cure the material. So when this material will be injected on the platform or the build tray, this is basically build tray, okay, on which we will inject this material. So build material will be injected on the build tray, and then we will switch on the UV light. So UV light, so that material will be exposed to the UV light, and then it will be cured. So what are the key developments in this area? So here, I mean, this particular technology is relatively new. Okay. So here the Stratasys and the object connex machine is actually there. Okay. So Stratasys actually is making this kind of printers, right? So what are the benefit with this material jetting process? The multi-material and multi-color. So we can have parts with multi-materials. Okay, and also we can have the multi-color. Okay, in the case of material extrusion, sometimes if we use the dual nozzle for part manufacturing, then we can have only two colors. Okay, if we use three nozzles, then we can have only three colors. But with this material jetting process, we can have part with multicolor and multi-material. So this is one of the benefit. That's why people have started exploring this particular process, and people are doing research on this material jetting process. Okay, and I'm sure after few years, the people will start developing this kind of printer, and these printer will be available for at low prices. Okay. So here, in this particular technology, many traditional 2D printing companies are investigating 3D printing. So one of the company, HP, you all know about HP. Okay, so HP printer is also there in the market. If you search HP 3D printer, so that printer is also based on this particular technology, material jetting. So HP actually the name of that particular printer is the HP Multi-Jet Fusion. So the part quality of this particular printer is quite good. You can search HP Multi-Jet Fusion. Okay, so HP has already started manufacturing this kind of printer, and now HP is investing in the 2D printers, and also they are investigating 3D printing. So and people are also taking interest in printed electronics. So people are trying to print the electronic parts by using this material jetting process. Okay, so next is the key developments in binder jetting. So here, as I told you, here a liquid bonding agent, not build material, because previously what we were doing, we were injecting the build material from the jetting head, but here what we are doing, we are depositing the liquid bonding agent. Okay, why we are depositing? To join powder material. So powder material will be build material will be on the bed or on the build platform. Then we will deposit the bonding agent, right? So bonding agent means like we use the Fevicol or and other things, okay, in our daily life. So and similarly here we will use some special bonding agent. Okay, so here we will have the head, and you can see the droplets. So these are the droplets, okay, which are being deposited on the build platform. So already we will have the powder material, okay, on the build platform. Then we will deposit the bonding agent. So this bonding agent will help in the joining of powder materials together. So what are the key developments in this area? Means what people are exploring, and what are the developments which already have been done. Okay, so first is the 3D system. So 3D system is the very popular manufacturer who is making this kind of printer. So they are marketing color jet. So the printer name is the color jet. Okay, so color jet printer is there. So they are selling this printer in the market. So we can even we can print some sugary food. Okay, if grains are there, it means material is in the powder form, then we can easily bind that material with the help of bonding agent. Okay. Then ceramic, so pottery and the art application can be explored by using the binder jetting process, right? Then also color jet, this particular 3D system has announced a color personal 3D printer. Then X1, Exxon basically expanding the sand printing, and they are trying to build metal parts. So how they are joining metallic materials together or metal particles together with the help of bonding agent. Okay, so sand printing is also possible nowadays. So previously it was not possible, but now people have started exploring these sand particles. Okay, so sand particles basically they are joined together by using the bonding agent. Then we can make any kind of 3-dimensional objects. So another company is the Voxel Jet. So Voxel Jet and some other companies also there. So they are making this marketplace dynamic. Okay, so they are coming up with their new printers, and they are giving competition to the already available companies like 3D System. 3D System is one of the popular company. Okay, so nowadays more companies are coming up with their printers, and they are actually creating more and more competition in the market, right? So next is the directed energy deposition. Directed energy deposition. So actually these process actually focus on the thermal energy. Okay, that is used to fuse materials by melting as they are being deposited. So you can see here I have taken two pictures. Okay, so first this picture, the right hand side picture, actually belongs to the lens process, LENS, laser engineered net shaping, and the left one actually is showing the fabrication process by EBAM, electron beam additive manufacturing. Okay, so you can see here we are using 4 different nozzles. Okay, and then at the center we are using a laser beam. So that laser beam is focused at the center point. Okay, and by using these 4 nozzles we are depositing material in the powder form. So when the material is coming up is coming up through these nozzles on this particular part or on the surface, then the material is actually, or the powder particles are fused together, because laser beam is already there. Okay, because we are focusing laser beam from the center, so the powder particles will be fused together, and then we will have we will achieve the 3-dimensional printing. So nowadays this kind of lens process is being used for repairing purpose. You can find some video on internet. Okay, you can find any you can just type LENS, lens additive manufacturing, then you will find a lot of videos where people have used this lens process for repairing purpose and for the fabrication purpose. Okay, then EBAM, this is also getting very popular nowadays. So this is a relatively new process. Okay, and people are exploring electron beam for metal additive manufacturing, because previously only SLM process was there, selective laser melting, but nowadays these 2 processes are also added in the list of metal additive manufacturing systems. So lens is there, now EBAM is there, and also people are exploring some other type of system in which they are using friction stir welding principle in the additive manufacturing. So you can find some papers on this. Okay, then you can get some idea how they are doing and how can you proceed further. If you want to proceed in this area, then how can you go in this area. Okay, so this is one of the area in which you can start your research work, right? So this electron beam with wire, so the difference between these two is the the lens use the material in the powder form. However, the electron beam additive manufacturing process use the material in the wire form. Right, so you can see there are two type of wire actually are being deposited. Okay, so there are two system. Okay, two side nozzles are there, so they are basically feeding the material in the wire form. So electron beam with wire seems to be leading for part production currently. So what are the benefit with wire? The build time actually will be less. Okay, so we can fabricate three-dimensional object at much faster rate. Okay, as compared to the other process. So this Psyche is one of the company. Okay, so actually they have developed this particular technology. Okay, and now they are doing some improvement, and they are now they are in the market. Now the machine is available in the market. So now people have started purchasing these machines for their work. And also in this area, the manufacturers are marketing laser deposition head as add-on to the existing machine tools. So basically people these manufacturers are marketing a laser deposition head. So they are just selling deposition head. So those deposition head can be used as a add-on. So at the place of cutting tool, or at the place of the cutting tool, we can mount these deposition head. Okay, then we can start additive manufacturing. So this is a very running area in which you can start. You can come up with some new ideas. Okay, how can you convert your CNC machines or CNC milling machine into the additive manufacturing? So you can search the keyword retrofitment of the CNC machine tools, right? So in this course we will also have one lecture on metal additive manufacturing. So that will be delivered by the Dr. Sajan Kapil from IIT Guwahati. So he will focus on this kind of technology. Okay, he has also worked on this and he will explain you the benefit of metal additive manufacturing, and also he will show you the hybridization of additive manufacturing. How can we convert a CNC machine into additive manufacturing? Okay. So now what are the engineering implications? What are the implications in additive manufacturing? So here I have shown you some of the main driving force. Okay. So first is the more complex geometry. So if geometry is too complex, if you go back to the definition, then people used to say complex geometry can be make with ease through additive manufacturing, but it is not like that. Okay, so when we have a more complex geometry, okay, then it is very hard to fabricate exactly as per the CAD model, especially internal structures, right? And second is the what are the key traits basically here? What are the main obstacles to the commercial implementation? Why this technology is not available everywhere? In the industries. Why they don't think this technology is not useful for them? Why they think like that? Because of these things: repeatability of the process, reproducibility of the between the machines. Repeatability means if we have make the part from a printer. Okay, now if you want to fabricate the same part with the same machine, then there is no guarantee you will be able to get the same part or same kind of quality, because various factors are working. 3D printer is not that much simple. 3D printing is not that much simple as we think. Okay, and also reproducibility between the machines. So you have to study about the various factors. What are the factors which can affect the part quality, and what are the things which we should consider before going for part printing on the machines, right? Then Next is the quality of the product for the particular use. So first is the accuracy, second is the surface finish. Inherent porosity is also one of the problem. Okay, so this porosity basically affect the strength of the parts. So due to which you can see mechanical property. So if you compare a 3D printed part with the then that of means the part made by injection molding and other process, then you will find the difference between mechanical property. There will be huge difference basically, because in the injection molded parts the porosity is not available. Okay, but in the case of 3D printing, porosity is there. And also how means what are the means how you have means made your layer, what pattern you have used, and how you have means deposited material. So a lot of things are there. So first we need to understand all the factors, and then we should only go for part fabrication. So first we need to thoroughly understand the various factor, how the layer thickness can affect the part quality, how the pattern can affect the part quality. After that after developing some know-how about the process, then we can go for 3D printing. Build speed is also one of the factor. So what are the current business trends? Means in the domain of additive manufacturing, means how people are doing business. So many new business model actually are there in the market. Okay, now people can print parts at home, at a local print shop, or online. So online I can send STL to someone, okay, and he can print for me. Or else I can means print parts at my home for others, then I can earn some money. Also I can means open some local print shop, okay, where people will means come up and they will ask for printing. Okay, accordingly you can develop STL for them, then you can print for them. So there are new means business models actually are people are coming with some new business model, okay, based on 3D printing. Okay, and people are also means developing new machines. So as I told you, nowadays the machines are available at very low prices. Okay, so new machines are coming up, you can just assemble them. You means already means kits are there. Okay, so if you purchase that kit, then you can assemble all the components together, and then you can start your own 3D printing. Okay, patents, and why it is happening, because all the patents related to 3D printing are getting expired, right? And also means people are coming up with software tools. If you means search the different softwares for 3D printing, means for particularly means for material extrusion, then you will find a good range of software. Okay, like Cura is there, Slicer is there, Repetier Host is there, Simplify 3D is there. So a good range of software tools is there in the market. So people are also coming up with their new software tools. Okay, and in which you can see the different function. Okay, and then the user friendliness also is one of the means factor which affect the quality of a software tool. So nowadays means new software tools are coming. Okay, and people are investing means a lot of money in the development of software tools. So service providers also means are there. Okay, so various service provider, so they are providing means different type of services like STL preparation or model manufacturing. So different means tasks can be means completed by the service provider. Okay, even though they can manufacture a 3D printer for you. So different types of companies are developing within our country or across the world. Okay, who are dealing with the 3D printing. And also I know one of some of the companies are working on the filament development. So they are preparing filament of different materials and means under the Make in India campaign. Okay, and I am sure means under this Atmanirbhar Bharat mission, more companies or more means startup will be launched based on 3D printing, and they will come up with new ideas. Okay, and in near future, I think filament cost will be reduced, and you will get the filament of 1 kg filament is around for 500 rupees, 400 rupees, and it will happen within 5 years. Okay, within 5 years you will see this. So what are the challenges? Again, I'm just telling you, the material constraint is there. Okay, part size limitation is there. So I have suggested you the big area additive manufacturing. Okay, material constraint, you can develop some new materials for additive manufacturing. And also I told you about the toolpath patterns. So limited toolpath is there. You can explore some new means filling patterns. Okay, and you can explore them into additive manufacturing. You can come up with some new ideas. Then you can propose some new technique for surface finish. Okay, and again dimension accuracy, because shrinkage is there, warpage is there. So a lot of things actually, lot of factors are there. So you can consider these challenges. Okay, and you can consider them as a research project, and you can come up with some new ideas. Okay, and with this I want to stop my presentation. So if you have any question or any query related to this talk, then you are most welcome. Then you can raise your hand, or you can leave your comment in the chat box. So I will take your query one by one. Okay. Thank you. Yes, I think Chiranjeevi. Okay, first let me check the. Okay, Subramanyam Madhyastha. Okay, I am making you presenter. Okay, then you can unmute your mic. Yes, Mr. Subramanyam Madhyastha NR. So I have made you presenter. Now you can means unmute your mic. Then you can ask your question. So do you have any queries, Subramanyam? No? Okay. Thank you. Let me check the chat box if any queries there. Yeah, Mr. Chiranjeevi, you are asking about the missing triangulation. Okay, missing facet. Actually, you are asking about the missing facet, right? So I would suggest you for STL. So I think you are working on STL side. I think so. Okay. So I would suggest you you can explore the book which is written by, you can read the book which is written by C.K. Chua. So Chua et al. Actually one book is there. So you can refer that book for for the detail related to STL file. So he explained very well the different errors in STL file. Okay. So not only missing facet. So there are various issues with the STL file which you can experience when you will work on that. Okay, so you can refer that book. So I will give you the link or the name of that book, so you can download from the internet, or if you find it. Okay, and we have a separate lecture on the STL file, so don't miss that lecture. I think in the next session the sir is going to discuss about the STL file, and also he will tell you about the repairing process. Okay, so is there any more query? No? Any queries there, dear participants? If you have any query, then please ask. Otherwise, we can stop here at this point. So if you have any query, then you can ask. No? Yeah, you are Chiranjeevi. Yeah, you are asking about the lot of potential about the tool path and optimization. Yeah, so you can search about the different filling patterns. Okay, so there are various curve, okay, which are used to fill the area. Okay, like piano curve is there, and other curves are also there. So you can explore them, and you can develop some algorithms to implement them in the additive manufacturing. So one curve I am suggesting you piano curve, fractal curve already explored by some other researchers, okay, or also by me. So you can go with the piano curve. Anyone else? No? Okay, so thank you very much for your attention. And if you have any other query, then please you can write me in the WhatsApp group, or you can contact me through email. Okay, so my email ID is already with you, so you can write at any time. Okay, thank you very much. Okay, thank you all. So next session will be started at 2 p.m. Okay, so Dr. Prasant Kumar Jain from IIIDM Jabalpur, so he is going to discuss about the STL file, and he will also say some of the solutions which are related to STL file. How can you repair it, and how can you identify the different issues in the STL file. Okay, so thank you. I think one query is there, Dr. P. Prabhakar. Yes, sir. Sir, please ask.
Sir, no, nothing to specify, and already in morning session I had asked.
Okay, okay. Thank you, sir. Thank you. Okay, welcome. Okay, okay. Thank you, sir. Okay, so I think I have responded to all your queries. Okay, so thank you very much. So now we will meet again at 2 p.m. Okay, thank you. It's time for lunch. Thank you.
So very good afternoon, you all. I welcome you all in the post-lunch session of this online FDP event. Our expert, Professor P.K. Jain sir from IIITM Jabalpur will join us very soon, and so that our next talk can be initiated. So we are just waiting for Professor Jain sir to join, so that our next expert talk can be started. Am I audible to you all? Can you please write in the chat box so that it can be a kind of confirmation for me, so whether am I audible or not? Thank you so much for your response. Thank you, Taranjit. Thank you, Arun. Thanks a lot, Ankit. Professor Jain is just join our session very soon. He is just having some issues with the network connectivity and all. Okay, so just in couple of minutes he will join. I have just contacted him and he is just saying that in couple of minutes he will be here.
Within 2 or 3 minutes, as Professor PK Jain is trying to join.
Hello.
Yes, you are audible, sir. I'm just starting.
Mohit, actually, I think some issue with the laptop. I got connected with desktop. So,
Yeah. Partic- Professor Jain is with us. Sorry for delay. There was some technical issue in joining the Microsoft team. So before inviting the Professor Jain to deliver his talk on 3D printing, first I will like to introduce about some key facts of Professor Jain. Dr. Jain has over 25 years of research and teaching experience at UG and PG levels. He graduated in mechanical engineering from Dr. H.S. Gore University Sagar in 1995 and did masters in advanced production system from Sati Vidisha. He has received PhD degree in the area of rapid prototyping, additive manufacturing, particularly on part strength studies in selective laser sintering process from IIT Delhi in 2009. Dr. Jain was previously with the Delhi Technological University, Delhi, which was formerly known as Delhi College of Engineering, as lecturer in Mechanical Engineering Department. He has also served Indian Institute of Technology, Delhi, as a project scientist and research associate, where he was engaged in the research work on error compensation in CNC machines and part quality improvement in fused deposition modeling. Currently, he is with PDPM, IITDM Jabalpur as Associate Professor and Dean Students Welfare. Dear participants, Professor Jain has more than 100 publications to his credit, published in the international peer-reviewed journal of repute, national and international conferences in India as well as in abroad. He has guided 5 doctorate theses and 25 master's theses, and several theses at PG level and doctorate level are going on. He has been a resource person and delivered invited lectures, chaired scientific sessions in several national and international conferences, STTP and QIP programs, and so many different research platforms. His research interest extends from geometrical modeling, CAD-CAM, integration, increment sheet forming, computational geometry, rapid prototyping and tooling, incremental sheet forming to nanotechnologies in manufacturing. Dear participant, there are so many things more to explain about the Professor Jain, but due to the time limitation, I'm finding the features of Professor Jain with these key points. Now, I would like to invite Professor Jain to deliver his talk. Welcome, sir.
thank you, Dr. Mohit and Dr. Ravi Pratap, Dr. Narendra. Sorry for the delay. Still, I am not able to resolve the issues currently going on with laptop, some proxy setting or something else. But fortunately, I have got connected with my desktop. So let us resume the session. Okay, can you see my screen?
Not now, sir.
Okay, have you made me presenter?
Yes, yes.
It's not giving me right now the option to share the screen.
You are presenter, sir.
Okay. Can you see my screen now?
Yes, sir.
Fine.
Now we are seeing your screen, sir.
Okay. So now it is in presenter mode.
Yes, sir.
Okay, fine. So today's session we cap for this software solutions for 3D printing. Although we call it nowadays additive manufacturing process, and much standard term used by engineers, technical experts in this area. So we begin with, I hope on the very first day you got the introduction of 3D printing and additive manufacturing. So we will not go in today's session into the details of the process, etc. But let me take you to why the software solutions and error repairing of STL file and slicing, and even though a lot of softwares are available, open source softwares also available, but still we require a lot of programming to be done by ourselves. So in this, just begin with the like the CAD model. We can develop such CAD models in any software like ProE, CATIA, SolidWorks, UG. Then as per the process characteristics, we need to fabricate the parts on the layer-wise fashion. So we need to do the slicing of the object. And you see here when we go for the slicing of the objects, so we have like this objects, we can do the slicings like this, right? And we receive such kind of tapered edges. So we need to square them so that edges are squared, right? And the next step is to staking and pasting of layers. Right? So after these layers have been developed, then we go for the staking and pasting of the layers in this way, and then the result of this kind of physical product. Now look at this. This was the original geometric model. That is the physical model. We wanted to achieve this, right? But you see the result of, because of this layered structure, structure of the fabrication, you see we got a lot of this stair stepping effect on here. This leads to the poor surface finish, right? So here one can always argue like that we can have a minimum layer thickness, but we can't eliminate the layer thickness. That is the fact. So depending on the different processes like fused filament fabrication or any powder based process, liquid based process, wherever we have to have this kind of layered structure, the inherent surface roughness would be there. So the next step is the finished physical prototype, which requires a lot of post processing, polishing, grinding, etc. So this is all the principle where the software comes into picture. The first thing, the geometric model, then the slicing, you require a lot of programming or the commercial packages, then squaring edges, and then here also we require a lot of things. I will include this thing in tomorrow's session from my laptop, where we will talk this kind of situation is also we have to optimize it for the uniform allowances to be on all the sides, right? And then we move to the process chain. Look at this here, one cylinder, another cylinder. Can anybody notice what is the difference in these two cylinders, right? The first one is your uniform smooth cylinder, which we have designed in ProE, and another one is the tessellated model, right? So this tessellation is a piecewise approximation of the surface. So you can see this is the triangle and there is a planar section. So if we have any spherical surface even as well, right, we divide this spherical surface as well in a triangular planar sections, right? So now this will become a complete planar section, okay? Then we do the tessellation. This will help us to do the slicing, right, to achieve this step, right? So tessellation has nothing to do with the additive manufacturing, but we perform this tessellation in a software or by our own itself. Lot of algorithms are available, like Delaunay triangulation, Voronoi diagram, etc. Based on this, we perform the slicing. So what is happening here? The instead of a typical sculpture surface, like here, this is a cylinder. So if you cross section it, what we receive? We receive a circle, right? So this is quite simple. But suppose in my hand I have this kind of mouse or any other typical component, and if I sliced it, what is going to happen? A typical 2D contour would be there, right? So with the 2D contour, to obtain the 2D contour, we have to solve a lot of intersection problems, right? So look at this here. What is happening for this slicing? Now this problem is reduced to a simpler one, where we have a plane which is parallel to the XY plane. So we can define Z equal to, say, 5 or something unit, and then easily we can find out these intersection points. I will show you the MATLAB program, why I am emphasizing much on the programming in this session and tomorrow's session. So we do the first thing, the geometric model, then we do the tessellation, and this tessellation facilitates us for the slicing, right? And after this slicing has been done, right, we require to generate the laser path if it is a laser based technique, or if it is a nozzle based, then we require the nozzle path, right? And then we go for part fabrication, and then do the post processing or polishing or grinding or anything is required, right? So this is the process chain. Now you see how we implement this, right? You can see this is the geometric model created in Pro-E, right? Then you can see here, this is the tessellated model, right? So in the tessellation itself, you can see here this model is converted into the triangle. You can see here, this is the one triangle, this is another triangle. It's a planar section, so divided into two triangles. But here you see here the circular surface is there, so we have the lot of triangles, smaller triangles, so that we can reach out to the more close to the surface. Similarly, here you can see where is the, and the top surface you can see the simple rectangular geometry, so only two triangles are sufficient, right? Look at this for intersection. What is this? You can see here, this the green color plane is there, right? Taken at this height, and you can easily guess what is these. What are these blue dots, right? These blue dots are the intersection point with this line. So remember this, if I take a plane, the typical equations of this solid model is now reduces to the triangular plane, and that plane itself into three straight lines. So you see there is a STL file, and within that STL file, this is the triangle. Now our case is very simple. We can find out these intersection points, right? So you can see here all these blue dots are the intersection points of that plane, right? Now next is this connecting these dots in a logical sequence. What is happening? You see here, when I do this, and if I print like this, what is going to happen? This is going to be in a logical manner, and you see here all the points are connected, but this information is not at all useful for us, right? Why this is not connected in a sequence, right? So because of this reason, these points are not useful. So our next task is to that we should connect them in a logical sequence. Look at this next figure. In this case, what is happening? Right? So you can see here, this is the blue color dot, blue color contour is the external contour. Red dotted line is showing the internal contour. This is again external contour. This is internal line. So you can see if I cross section here, you will receive this contour inside this contour, and again two more contours on this. right? So in this way we can do. Now the next step is to get the nozzle path, right? So for nozzle path, what we need to do is see, look at this. You can easily see the inside the pink color dotted. What we have is the area which is to be solidified, right? In this area we have to solidify, so we have to deposit the material either by the laser beam, either by the nozzle path. So simply we can adopt the logic where this is intersecting this contour, we can switch off on the nozzle. Up to this point we can deposit the material, right? Here we can switch off the nozzle, here we can again switch off the nozzle. So alternate we can do this kind of. So for this programming, this software solution lead us to that point that we can generate the nozzle path using our programming, right? So this is all about the data preparations, right? Now look at this Magix screen. You can see here how this is working, right? Let me show you this Magix screen. Somebody please confirm if it is visible, the entire screen.
Visible, so visible.
Because in this team I cannot see even my own video and the participant screen. So sometimes it seems completely blind. Can you see this screen, the software screen?
Yes, sir.
Thank you. Okay, let me find, because since I am using my desktop, so maybe let me search the yeah, can you see there are ball inside ball?
Yeah, yes, sir.
3 balls are there, and you can see on the bottom it is written the IITD. Here we require a lot of manipulation of STL file. This is originally designed by EOS, but you can see on this side you have a lot of the triangles, the window, the shell, the surface, edge, expand, shrink, so we can cut different STL files, different triangles, we can stitch them, we can identify where is the hole. We will come one by one on all these kind of defects, etc. But look at in this case, right? And then let me put it on the section, right? You can see here this blue color contour you can see, right? And here you can see the lot of triangles are there, right? So these triangles are the STL file triangles. Look at this, right? These are the small triangles which help us to calculate the intersection. And you can see on this screen here the blue color contour is there, right? So this blue color contour is because of that this logically arranged we have point. If we have cross section over here, we will receive 1 point here, 1 point here, like this. And these are the random points. In a STL file, we don't know in what sequence they are arranged, all the triangles, right? So once we arrange them in a form of a sequence, we will receive this kind of information, right? So this is the contour information we receive. And look at this. Let me put it again in the section mode. So this will start like this. This is the first section, second layer, third layer, like that number of. So you see in this portion it is getting a circle. Now see in this portion only some part of the spring will work. right? So solidification will be done only in this region where this contour information we are getting, right? You can see here, this is the information we can get, right? Cut section. Okay, right? And then we can proceed in this way. So you see here at this point only the one sphere is built, right? And if we talk about the SLS process, I hope you already gone through the different processes. Right? So in this way you can see right, and if we keep on moving you can see here like this. Now you see the second sphere in picture, and in between there is unsintered powder which provides support so that you can we can print on this, right? And you can see the contour information, right? And if we continue to print like this, you see the third sphere coming into picture. They are not joined with each other because unsintered powder is providing support in between them, right? Look at this, and by this way you see here at this stage the first sphere is complete, right? Now first comes second, third, like you see the part is completed, right? So we require this contour information at this stage, and look at this. This is all the triangles need to be connected. The intersection points need to be connected. See here, you can see here these points are to be connected. You can see this is the intersection point, this is the intersection point where these triangle lines and these points are connected by this straight line to get the complete contour information. Right? Is this okay? Right? So other things regarding to this software and other things we will take a little later. Let us move further. My PowerPoint screen is visible now. Is it so? My PowerPoint screen is visible now. Dr. Mohit, Dr. Narendra?
Yes, sir. Yes, sir.
Yeah, my PowerPoint screen is visible.
Not visible, sir. Now. Abhi chala.
Now?
Yes, sir. Now it is visible.
Okay, thank you. Thank you. Yeah, I'm all. Okay, it's not working. What is happening? Fine. So look at this. This is the geometric model originally, which we have modified it. Right. Now come to the STL file. This is entirely on the STL file. So all slicing to be done on the STL file. This is already industry standard. So we have already discussed about this cylinder, right? What is there in this cylinder? You see, we have already tessellated this model, right? That's the difference you can clearly identify over here. right? So you can see in this rabbit portion also, you can see a lot of triangles are there. These are the uniform size, and here we can vary the size of the triangles, right? So what we contains in the STL file, right? See, for example, you have on your screen a cuboid, right? 5 by 2 by 3 units, right? So what we do, we did the triangulation of it. So every face is now divided into a triangle, right? So this represents a 3D surface geometry, and that surface is tessellated logically into a set of oriented triangle or triangular facets. So here some rules are there. So in this case, what is happening, each facet is described by a unit outward normal. There would be a normal outward to each and every facet. For this, here is the normal. This will have the same normal like this. So one normal and 3 points, 1, 2, and 3. So 3 vertices would be there and one normal. That we write in a form of a STL file. So you see, if we open an ASCII file of an STL file, it will look like this. Right? So these are some consistency rules, like if you remember the Euler's formula, the number of faces must be even. Say for example, a cube, how many faces? 6 faces, and all these 6 faces would be a square. Right. So if you make a square in this case as well, then you will get the 12 faces. So the faces will always be a even number. Then the number of edges must be a multiple of 3. And 2 times the number of edges must equal 3 times the number of faces. It's simple Euler's formula to check the consistency and validity of a solid. Okay, then look at that. This stands for the standard tessellation language. Early stages and in the start of the 3D printing as a liquid-based stereolithography process, right? So this format has already become the standard for rapid prototyping, 3D printing, or we can say additive manufacturing standards, right? So it's all a series of polygons corresponding to different Z value. And what is our requirement? Our requirement is to get the 2D contour, closed 2D contour. So this STL file is capable of generating those 2D layers, right? So this serves our purpose for the 3D printing. Come back to again, what is it contains now? 12 numbers because of the 3 XYZ, XYZ, XYZ for 3.9 numbers and CX, CY, CZ for the normal, right? So, and further this, the orientation is managed like this, outer. This is counterclockwise and this is the normal. So normal would be outside and this is the counterclockwise. Even though we can say it is redundant, but we follow here the right hand rule. The all files of the STL file are written in this way, right? So some other rules like each triangle must share 2 vertices. Right, these are the 2 triangles and you see 2 vertices minimum will be shared, right? If this is the triangle, you see this vertex is shared by 1, 2, 3, 4, 5 triangles, right? Similarly on the bottom side it may be 6 even also, but minimum 2 triangle it will share, right? Similarly the all this is now redundant. Then we have 2 formats to write the STL file. One is in the ASCII format, more descriptive, human readable, but contains very large size of the CAD data, right? So then another one, we have the binary. So you look at this, we have this binary data, and you see the file, this is the binary. So the file size 12 triangles 684, but it have very large data. The same file 12 triangles, but it contains 3400 bytes, right? So this is basically machine language. We contain 0, 1 kind of information, and ASCII is the human readable file. Now see, this is how we write the STL file. Right here, the different structures are there. So let me show you how the STL file is exported by various software. If I export this file from CATIA, the structure may be different. If I export this file from say ProE, may be different. AutoCAD may be different. Or it's a specialized software like Magix, it may be different. Look at this. See, there are two files. This one is and you see the difference in these two file structures. This is from AutoCAD and this is from Magix. In both cases, we have capped its cube at 0, 0. Look at this. Here, this all is indented. The file is indented, right? And here everything is left aligned. This is from Magix and this is from SolidWorks or AutoCAD. Another difference you see, this is the decimal numbers, right? And here are the scientific numbers used in this way, right? So when we write a MATLAB program to read this STL file open in MATLAB, this becomes different. And this I will show you again. We can read it clearly. This is where the corner at the 0 point, and this is where the corner at the center. Let me show you this on the MATLAB screen. Sorry again, since I'm using now this, so let me open the file. Look at this. If I use this file, SolidWorks AutoCAD, so you can see here on this side, these all are the XYZ values and the normal. First is the normal and the XYZ for 3 coordinates, right? You can, I hope you can see my MATLAB screen. And look at the figure. You can see here, this is the cube, right? And the next part today, maybe tomorrow, I will tell you how to find out the cross section and the 2D contour of this cube, right? So in this case, if you look at this, its corner is at 0, 0, right? And look at this, if I use this file, right? And try to open the same STL file. We have used this. There is an error, right? Because this file, you can see here, this structure is simple, right? Just like your C file. So you are just scanning the entire Word file. It's a small program. This is for plotting and patching, right? Otherwise, this is the main program. right? So in this case it's not working, but this program is specifically changed to read that magics file where every text is aligned to the left. Sorry, I think in this file I may not have the queue. Okay, let me move. Cube magics, right? You can see here, this is the cube magics, that magic software. So you can see here it's center at origin, right? Let me put it on. See, like this. So center is at 0, 0, one file I was showing you, and another, if I run the same program and use, sorry, since I have changed the folder, let me go back. Corner at 0 point. So you can see here, if I go for the corner at 0, look at this. This time corner at the 0, 0 position. Right, now let us go back, and now this is, since human readable, we can read it on our screen as well. So look at this, you can easily see this is the normal. You can see here, right, 0, 0, and the coordinates value will become now 10 because your cube is defined like this. So this was your 0, 0, so all this side will become 10, 10, 10, 10, right? And here, because of the center, so what has happened, center is at the origin. So what happened, this side 5, this side 5. So you can easily read, and even you can edit this STL file if you know very well what is the meaning of different text, right? So you can even edit the dimensions of your STL model here in this case. Even without having ProE-CATIA or any other thing, if you wish, you can even write the STL file for 3D printing, right? But you should be very good understanding of the STL files. So before going for any object to be 3D printed, we should be very good in understanding and handling of STL files, right? Now we come to the advantages of STL file. See, very simple to understand, very simple to code. Then any kind of geometry we can tessellate in the STL, and we can form using the RP machine. And almost it's a de facto standard. Everybody is using like that, right? And the disadvantages of the STL format also there, right? What is happening even for a cube, right? We can define easily with a 6 facets, but what is happening? We are using 12 facets, right? So here what the problem comes, we already discussed the STL file, even though we use the binary, sometimes it can be very high in the size, even with the original part. If you store this .prt or .catia file, .proe file, anything, that the STL file may have the size larger than that. So look at this here, the STL file many times larger, and then STL file carries much redundant information, duplicate vertices, edges, right? So because of the reason like that, you see here the common vertices may be shared by the 6 faces. So it will come on, and the same vertices will come into the 6 faces, right? Similarly, you see this edge will be used by this triangle as well as this triangle. You can see here the single vertex is required, but it is used by 4 nearby triangles. So 4 times it will be written in the file. So we will have much redundant data in a file, right? Say for example, you see here how many total vertices are required on this cube. We have the 8 vertices actually, but we write the 12 facets. So for 12 facets, 3 vertices for each facet. So we will have total 36 vertices instead of 8 vertices, right? So that's the too much redundant data it will carry, and that's the reason the file size will become very big, right? And you can see here the same geometry. This geometry and this geometry both are same, but what has happened here, this is approximated or the tessellation done using 8 triangles. So the file size is 2025 bytes in ASCII format. But when we wanted to move to the more close to the surface, right? So we are forced to use to the smaller triangles. For these smaller triangles, what is happening? The 944 triangles are there, and the file size reaches to the 2,67,000, right? So in a GB's file reaches to, right? So that's the problem, variation in the number of triangles for different geometry, right? And the overall dimensions are approximate by the same thing. So what is happening here? We control the number of triangles by the software itself. So 2 parameters are there: chordal deviation and the angle control. Based on these 2 parameters, this is the STL file output parameter from the SolidWorks. This is the screen of the SolidWorks, right? So based on these 2 parameters, say for example in a 2D case, I see this. Now we have to approximate in a planar section. So I can see in the top view, I will see a straight line. This is the planar section, right? Now this distance, if we control this distance, what is this distance? This is the chordal distance, right? Similarly, we control the angle as well. You see, based on this, what is going to happen? By controlling this parameter, you see here the deviation is capped minimum and angle is also capped as 30 degree. This is the result, and you can see the number of triangles are 668, right? And the file size is 1,89 bytes. Now look at in this, the deviation is, and the angle is also reduced to 30 degree. What is happening? Both these things we reduce. This is in reverse order. So you see the number of triangles are increased. Instead of 600, now 1000 are there, right? See, in this case, further we reduce the angle. The deviation is kept same, but the angle is further reduced. What is happening here? You see the number of triangles are also increased. Now around 1400, and here 3,90,000 bytes in this, right? So the file size is increased more, right? And number of triangles are more, the file sizes keep on increasing. But in all this, what is happening seems very good. We will be able to print the 3D part, but there are a lot of errors as well, right? So quite chances are there when we export the STL file, this may be the bad STL. Dr. Mohit, we can take up some questions here at this stage. If any participant have any question. or else we can continue with this some errors, and last 10-15 minutes we can devote to the questions. हाँ सुजय सर, आप आगे हो क्या? ओके ओके, मैं भेजता हूँ. बंटी ऑफिस आओ जरा. दो सिग्नेचर रहेगा जी, सूर्य सर और नेहा जीना. सूर्य सर बैठो, जीना सर मिल जाए तो ठीक, नहीं तो वापस आ जाओ. Okay, so let us continue with this, the reason for the bad STL, right? So what we discussed in a starting phase, the first rule states that adjacent triangle must have two vertices in common, right? And the orientation of the triangle, what side of the triangle is in and what side is out, right? So these two things are there, and this has to be agree with the normal. And if any of these criteria are not matching, right, so the problem would be there in the STL file. We call it the bad STL, right? And you see the existing softwares are there, right, but these STL file does not contain any topological data, so quite possible the vertices are connected in a different order. So many commercial tessellation algorithms are available, right, by different CAD vendors, but they are not robust, and as a result they tend to create various polygonal approximation models which exhibit the few errors like this. The gaps, cracks, punctures. Then we have the overlapping facets, then we have the non-manifold topological conditions, right? So let us see one by one. First we have the gaps kind of thing. When we have this kind of situation where the two sharp edges, two sharp surfaces are meeting, quite possible we have this kind of situation. Right, so you can see here this F1, F2, F3, this facing showing is the gap, and more clearly you can see here, you can see the top surface and this side the cylinder. So quite possible this gap is created because of the large tolerances we have chosen, right? Because of the large tolerances, this might be within the limit. Suppose we said 2 millimeter is the deviation possible, and this distance might be 1.5 millimeter. So here the no triangle has been created. Otherwise, it has to be created like more smaller triangles like this, right? So this kind of situation will occur. So here this is one is the missing facet or gap during the large curvature of the surfaces. This is quite possible that we have this situation. Then we have the degenerate faces. Similar thing again can occur like this. If you can have, you see here the large facets is there, right? So because of that, even it may try to fill a triangle over here. So because of this, this may create a triangular facet in which all 3 points seems like collinear in this way. Right? So all 3 points will become collinear in this way, and what will happen? This kind of triangle will be treated as degenerate triangle. Right? What is the problem if we have such kind of degenerate triangle? Right? The issue lies in this case is that where is the normal lies? Right? Now no normal. We cannot calculate the normal. Right? Because it will give you the infinite normal. It will become a straight line, and on a straight line, if you calculate a normal, you will receive at 360 degree, anything would be a normal. Right? So we will not be able to understand which surface area is inside, which surface area is outside. Right? Then we have the overlapping facet issues. Right? Due to the, say for example, for me, if I write say 8.3, this may be the coordinate for this, right? For you, you may write it 8.34. For someone else, it may be 8.46, right? Because of these, for computer, this is all different. This is 1, 2, 3. These all 3 values are different. Right? We may put the rounding off, and we can conclude this everything is equal to 8. But if we are not putting, what is going to happen? This point is there, this point is there, this point is there. So for different triangles, we will receive one value from this triangle of this vertex, one value from this triangle, one value from this triangle. Right? And we receive the different values of this point from the different triangles, and when we try to formulate this triangle, what is going to happen? Because of the different value, we will get the multiple triangles at this situation, and this situation will create multiple triangle but multiple faces, right, in this 3D space. Right? So that will create another problem, and this we known as the overlapping facets. Right? So we have to set while tessellation this tolerance, etc. Right? So I think we can stop at this stage, and different common errors we can take it in tomorrow's session. And let's keep this session open for the question answers participants have. Yeah, Dr. Mohit.
Yes, sir. Yes, sir.
Yeah, can we keep the session open for question answers now?
Yeah,
definitely. The remaining part we can take in tomorrow session.
Yeah, definitely, sir. Definitely. Some of the participants have already been asked some questions, sir. So just I will just read them for you so that you can respond them, sir.
I think I have closed the screen sharing, right?
Okay. Yes, sir. Yes, sir. It is closed now. One of our participant, Mr. Chiranjeevi from Bengaluru, I think, he's writing when 3D printing started, it was computer intensive to directly convert the 3D model to Z code. I think he just want to some like a history of that. I think he's interested in that.
Right now, initially what happened, what we discussed so far, we require a 2D contour information and then the nozzle path, right? So for nozzle path, if you look at that, yeah, now some open source softwares are available, and once this FDM printer FDM patent has expired, now many people are developing low cost 3D printer using filament technique, right? So they are using G code just like your CNC machines, right?
Okay.
The idea is behind it how that G code will come, right? So that G code will come from the STL file. This is true, the every solid model to be converted into the G code. But what are the various steps reaching up to the G code is that first the solid model be tessellated, piecewise approximation of the surface, then slicing. So that slicing will give you the 2D contour, and then you need to generate the nozzle path, right? Now it comes to the hardware part, how your nozzle will keep on moving. Right, so that nozzle path has to be keep on moving, and then we have to convert this into the G and M code. That's true. Yeah.
Thank you, sir. For another query, I will just read it. Yeah, another query is, sir, how do we solve the issue of missing faces oblique gaps when we export the STL file from one software to another, or what is the common practice used for this problem?
Okay. Normally, you can say the lot of commercial softwares are available to do that activity. But tomorrow's session, I will take you what are the algorithm. As an engineer, and if we want to continue our research in this additive manufacturing area, we should learn, we should know what kind of errors in the STL file and how actually they are resolved. Software can do anything for us, but tomorrow's session we will discuss the different algorithms and how to find out the missing facets. This will be extended session of today's session, and then we can show you how we have done it in the MATLAB to repair the STL file and then do the slicing as well. Both the things we will discuss tomorrow to find out the missing facets and fill that gap.
Okay, sir, sure. Okay, sir, these were the queries, those were just written down by the participant. Okay, one more is there. In principle, we can never limit. Okay, he's just discussing some of their own beliefs, like he's saying that in principle with STL we can never eliminate gaps but get finer and finer as the triangulation gets finer.
No, not necessarily. Not necessarily. We can, since we are using the approximation word, right? So we can completely fill. And before doing any tessellation or any slicing, slicing to be done, it should be a closed volume. So it is completely necessary. Whatever the fine STL file, small triangular you can take, but it should be a closed, right? So this is required. It is must. There should not be any gap. If there is a gap, we cannot create the nozzle path, right? I said earlier, we cannot eliminate the stair-stepping effect, right? Because there would be a layer, right? So if I have an object, let me show you, say this object, right? So in this object, if you see very closely, you can see there is a stair-stepping effect is there, right? On this side, since this is a tapered path, you can see here a lot of surface waviness you can see here, right? So that is because of this reason we cannot eliminate the stair-stepping effect, but we need to fill all the gaps. Without that, we cannot proceed for slicing, even though we get the finer and finer triangulation, right? I will tell you this again tomorrow.
Yeah, definitely, sir. Yes, sir, these were the queries. If any of the participants would like to ask directly to sir, they can raise their hand so that I can unmute them if you want to ask. Okay, sir. I think most of the queries you have already been.
Yeah, Dr. Mohit, I would request tomorrow's session, we can keep it in two parts. So in between, after 20-25 minutes, we can take some of the queries.
Yeah,
And,
yeah,
and
definitely.
then we can again continue our session, and then again and let the participant ask their queries directly by unmuting.
Yeah, definitely, sir. Definitely. Okay, sir.
Thank you very much. Thank you all the participants.
Thank you so much, sir, for this wonderful talk. Definitely, the participant will get benefited with the wonderful research perspectives you discussed with our participant. Thank you so much, sir. Thanks a lot. Okay, dear participants, we are just ending our today's all the sessions over here. It was completely very nice talk by Professor P.K. Jain, sir. Okay, so we will meet tomorrow sharp at 10 a.m. So then the fresh talk for today's tomorrow's session can be initiated. Thank you. Thank you so much. Okay, sir. Thank you so much.